The night is quiet. The world outside is wrapped in velvet darkness. And here you are, gently drifting into the realm where curiosity and calm meet. Welcome, dear dreamer, to the Dreamy Scientist. Tonight, we will follow a question that has pulled at human minds for generations. What is inside a black hole? They say a black hole is not just empty space. It is a place where time, and meaning, twist into something almost beyond imagining. A silent, invisible heart of the cosmos, pulling in all that dares to come too close. In this story, we will wander from the first whispers of the idea, through the birth of the black hole itself, to the deepest, most secret place at its center. We will meet the stars that give them life. We will feel the slow pull of gravity's hand. And we will linger in the shadow, peering past the edge where no light escapes. So, breathe deeply. Let the outside world fade. And together, let us begin our journey toward the dark, quiet heart of the universe. The story of black holes does not begin with high-tech telescopes. It begins with quiet human wonder. Long before physics had equations for gravity, before astronomers had lenses to magnify the stars, people looked up at the night sky and felt something. A pull. A question that seemed to have no end. Imagine a campfire burning thousands of years ago. The air is cool, the wood crackles softly, and above, the sky blooms with countless stars. No city lights hide them. They are sharp, endless, and impossibly far. Someone, perhaps an ancient storyteller, points to the brightest star in the sky and wonders aloud, what lies beyond? That was the first whisper. Not black hole as we name it today, but a sense that the universe might have secrets hidden in the darkness. Shadows in myth and story. Ancient cultures often told stories about the sky swallowing things whole. The Norse spoke of wolves chasing and devouring the sun and moon. In Hindu mythology, Rahu, the severed head of a demon, was said to consume the sun during eclipses. In some Native American traditions, a great cosmic bear would block out the light. They were not speaking of black holes, but their imagery, the darkness that takes without returning, feels strangely familiar. We might smile at these myths now, but they were humanity's first way of giving shape to an invisible force. Even then, people sensed that the universe contained places or beings from which light itself could not escape. In their own poetic way, they were circling the truth. The first glimmers of a scientific idea. Fast forward to the late 1600s. Isaac Newton had just described gravity not as a mystical pull of gods or spirits but as a law of nature. He showed that the same force that makes an apple fall also holds the moon in orbit. It was revolutionary. And it planted a seed. If gravity could pull on the moon, what if it could pull so strongly that even light could not break free? In the late 1700s, two thinkers, John Michell in England and Pierre-Simon Laplace in France, asked exactly this question. They imagined a star so massive, so dense, that its escape velocity would exceed the speed of light. Michell called them dark stars. Light, he reasoned, would fall back to the surface, making the star invisible. The concept was astonishingly close to our modern black hole, and yet, the idea drifted into obscurity for more than a century. Why? Because at the time, light was thought to be made of particles, and no one knew the true nature of space-time. Without Einstein's future insights, the dark star was more of a thought experiment than a physical reality. The universe was too quiet about it for decades. Astronomers had no evidence such objects existed. The universe didn't give them any hints, or so they thought. Stars shone brightly, planets moved in graceful paths, comets swept across the sky. No one could see the silent places where light disappeared forever. And perhaps that's why the whispers faded. Until the early 20th century, the notion of an object that could trap light felt almost fictional. Science had many other mysteries to chase: galaxies, nebulae, the expanding universe. The dark star remained in the attic of forgotten ideas. The quiet return of the whisper then came 1915. Albert Einstein introduced his general theory of relativity, a masterpiece that reimagined gravity not as a force, but as the bending of space and time. Suddenly, Mitchell's old idea could be reborn. Relativity didn't just allow the possibility of light being trapped, it demanded it, under the right conditions. A German physicist named Karl Schwarzschild was the first to solve Einstein's equations for a single, perfectly spherical mass. In his solution, there was a mysterious radius, a boundary beyond which nothing could return. Schwarzschild himself didn't call it a black hole. No one did, not yet. But the math had spoken. The invisible had a shape. Still no eyes to see them, but even with this, astronomers still couldn't point to the sky and say, "There, that's one." There was no way to detect something that emitted no light. Black holes, if they existed, were perfect hide-and-seek players. And so, for decades, they lived in a strange twilight space between theory and belief. They were possible. They were elegant. They were frighteningly beautiful in their logic. But they were silent. The human pattern of curiosity. There's something very human about this stage of the story. We often sense something before we can prove it. A poet feels the pull of the moon before an astronomer maps its orbit. A musician hears a melody before writing down the notes. A scientist imagines the invisible before building the tools to reveal it. The first whispers of the invisible were exactly that, soft, almost intangible. Not the loud, confident declarations of discovery, but the quiet hum of an idea that refused to die. The black hole without a name. It's worth remembering that the term black hole didn't even appear until the 1960s, coined by physicist John Wheeler. Before that, they were called frozen stars, gravitationally collapsed objects, or still dark stars. Names matter. They shape how we feel about a thing. And perhaps black hole was the name that finally allowed the public to feel the mystery in their bones. But we are getting ahead of ourselves. In this chapter of the journey, our ancestors, whether gazing from ancient campsites or Victorian observatories, were still standing at the edge of understanding. They had only begun to imagine a place where the rules we live by would break down. Why the whispers matter. Why linger on this slow beginning? Because every scientific truth begins this way. Not with the flash of a photograph or the click of a datagraph, but with a quiet wondering. The black hole began not as a telescope image, but as a story by the fire, a hunch in a notebook, a line in a letter from one scientist to another. We are heirs to those whispers. When we look at the Event Horizon Telescope's famous image today, we are not just seeing data. We are seeing the continuation of a conversation that began thousands of years ago. And now, the whispers grow louder. In the next part of our story, we will follow the clues the sky began to give us, the hints that the invisible was not only real, but closer than anyone dared to believe. The night sky has never been silent. It does not speak in human language, but in the steady glow of stars, in the slow dance of planets, in the occasional flare of a comet's tail. For most of history, these were the signs we learned to read. Yet hidden among them were subtler signs. Signs that something strange was out there. The whispers we heard in our last chapter, the first faint imaginings of dark stars, were still echoing. But now, astronomers began to hear something more. Hints. Clues. Puzzles that didn't fit the simple, predictable order they had come to expect. The light that disappeared. Imagine you are an astronomer in the late 19th century, scanning the sky through a polished brass telescope. You know the constellations like familiar friends. You've charted the motions of the planets, their orbits timed like clockwork. But every now and then, something is missing. A star that was once visible in your records is now gone. Perhaps it exploded, you think a nova or supernova. And yet, in some cases, there is no glowing debris left behind. Just nothing. To most observers of the time, it was a curiosity, nothing more. But a few, a very few, began to suspect these vanishings were more than cosmic coincidences. Binary star mysteries. Then came the binary stars. Pairs of stars bound together by gravity, locked in mutual orbits. By studying their light, astronomers could infer their masses, distances, and even the speed at which they circled each other. But some binaries played tricks. One visible star would dance in a strange, tight orbit, yet its partner was nowhere to be seen. No flicker of light, no faint shadow. And yet, something massive was clearly pulling on it. It was as if a ghost star, dark, silent, and incredibly heavy, was there, tugging at its partner. In those days, the word black hole didn't exist. But the riddle was already written in the sky. The gravity we couldn't see. The universe is full of light, but it is also full of invisible gravity. Astronomers began noticing stars that moved in ways they shouldn't, accelerating toward empty space, or bending their paths as though pulled by an unseen anchor. Of course, there are many invisible things in space: cold gas clouds, faint dwarf stars, but some of these gravitational pulls were simply too strong for such ordinary explanations. These invisible masses were rare, but each one was like a whisper getting louder. It was as if the universe was telling its story in reverse, showing us the effects before letting us glimpse the cause. The first X-ray clues. By the mid-20th century, we had something ancient astronomers did not: X-ray astronomy. Satellites equipped with X-ray detectors began finding powerful sources in deep space. One of them, Cygnus X1, would become a legend. At first, it was just another point of invisible light on a detector screen. But detailed study showed it was an intense, steady emitter of X-rays, paired with a visible blue star. The visible star was losing matter, and that matter was spiraling inward toward its invisible companion. Only something incredibly compact and massive could do that. And for many scientists, Cygnus X1 was the first serious candidate for a real, astrophysical black hole. Patterns in the chaos. You might think discovering something as dramatic as a black hole would be loud and obvious. But nature often works in the opposite way. The sky didn't announce black holes with fireworks, it teased us with patterns that only the patient could see. A star's brightness flickering in a rhythm too quick for a planet to cause. An orbit too tight for an ordinary star. Gas heated to millions of degrees, releasing X-rays from an invisible source. Each piece was small, almost insignificant alone. But together, they formed the outline of something astonishing. The riddles we mistook for answers. Not every riddle led straight to black holes. Some strange motions turned out to be neutron stars, the collapsed cores of massive stars that were not quite dense enough to become black holes. Others were white dwarfs, the Earth-sized remnants of smaller stars. But these false alarms were not failures, they were part of the learning process. Each taught astronomers more about the extreme lives of stars, and narrowed the possibilities for what might create the most extreme of all, the black hole. The sky had always been speaking. Looking back, we can see that the signs were there long before we recognized them. Ancient astronomers saw stars vanish without knowing why. 19th century observers charted strange stellar dances without guessing their hidden partners. 20th century scientists detected invisible gravitational pulls and thought them rare curiosities. In truth, black holes were always there, quiet, patient, leaving only their fingerprints on the fabric of the cosmos. The listener's perspective. Here's a thought: the sky speaks the same way to us now as it did to our ancestors. It does not change its language, we change our ability to listen. And to listen well, you must be both curious and still. In the stillness of a clear night, away from noise and city light, you might imagine the slow orbits of binary stars. You might picture a visible sun pulled into an endless waltz with a partner that has no face. You might realize that much of the universe is made of things you cannot see, only feel in the way they shape the light around them. And maybe, just maybe, you'll hear the riddle the way the first astronomers did, not as a problem to solve, but as a mystery to live with. A riddle waiting for the answer. By the mid-20th century, astronomers were closer than ever to naming the riddle's answer. Relativity had given them the mathematics. Observation had given them the suspects. Technology had given them the ability to see the invisible, not with eyes, but with instruments tuned to the hidden parts of the spectrum. And yet, for all their progress, the heart of the riddle remained hidden. To solve it, they would have to go beyond looking at the sky. They would have to imagine what it would be like to fall in. In our next chapter, we will step into that moment, the birth of the black hole idea, not just as a theory, but as a living part of astrophysics. We will watch as the pieces fit together, and the whisper of the invisible becomes the name we know today. The birth of the black hole idea. The night sky is full of old ideas reborn. The planets, for example, were once seen as wandering gods. Later, they became worlds with landscapes, weather, and moons of their own. Comets were omens, then icy travelers. And in the same way, the dark star of John Michell and Pierre-Simon Laplace would, centuries later, reappear, not as a curiosity, but as a necessity. This is the chapter where the black hole stops being a poetic musing and becomes a scientific creature built from equations, sharpened by evidence, and given the power to bend not only light, but time itself. The equation that bends the universe. It begins in 1915, with a man sitting at a desk in Berlin. Albert Einstein is thin, restless, and utterly consumed by an idea: gravity is not a force at all, but the bending of space and time by mass and energy. He writes the field equations of general relativity, a mathematical framework so elegant and so strange that it will take years for even other physicists to absorb its meaning. In it, there is no invisible pull like Newton imagined. Instead, space is like a flexible sheet, and matter like a weight pressing into it. Planets do not orbit because something tugs on them. They orbit because the space they move through is curved, and they are following the straightest possible path within that curve. A solution from the battlefield. Only weeks after Einstein presents his new theory, a German physicist named Karl Schwarzschild writes to him from the Eastern Front of World War I. Despite the grim conditions, Schwarzschild has solved Einstein's equations for the simplest case, a single, perfectly spherical mass. The solution contains a strange feature: a radius at which the equations break down entirely. Cross that radius, and the math says nothing can come back, not even light. Today, we call that boundary the event horizon. In Schwarzschild's time, it was just a mathematical curiosity, a singularity in the equations. Even Einstein himself thought it was a bit of a mathematical quirk, not a real object. The reluctance to believe. You might think the moment Schwarzschild's paper appeared, physicists would have shouted, "We've found the black hole." But they didn't. The idea felt too extreme. If such an object existed, it would mean a mass compressed to an infinitely small point, a singularity. How could nature allow something so absolute? Even Einstein himself, for all his vision, argued that such collapses could never happen in reality. The universe, he believed, had ways of preventing such extremes. Stars with no floor. In the 1930s, the conversation shifted again. Physicists like Subramanian Chandrasekhar studied what would happen when massive stars ran out of nuclear fuel. For small stars, the collapse stops at a white dwarf, dense, but stable. For bigger stars, the collapse goes further, to a neutron star, denser still, where protons and electrons merge into neutrons. But Chandrasekhar's math showed something terrifying: beyond a certain mass, there is no known force strong enough to stop gravity. Collapse would continue, endlessly. It was as if nature could build a floor in some cases, but for the heaviest stars, the floor simply didn't exist. The Oppenheimer-Snyder realization. In 1939, physicists J. Robert Oppenheimer and Hartland Snyder published a paper describing, for the first time, the full gravitational collapse of a massive star in Einstein's framework. Their conclusion? A star above a certain mass would collapse forever, forming what we would now recognize as a black hole. They described how, from the outside, the collapse would appear to freeze at the Schwarzschild radius, the surface seeming to slow and dim, forever stuck in time. But from the star's own perspective, it would plunge inward past the event horizon, into a region where space and time swapped roles, heading inevitably toward the singularity. It was breathtaking. It was terrifying. And it landed in scientific journals with barely a ripple. Why? Because 1939 was the year war erupted again. The world had other concerns. The black hole idea went quiet once more. The resurrection of the idea. The silence lasted until the 1960s, when astronomy itself began to transform. New instruments could detect not only visible light but also radio waves, X-rays, and gamma rays from space. Suddenly, the sky looked different, stranger, more violent. Quasars were discovered, incredibly bright and distant objects powered by something no one could quite explain. Neutron stars were confirmed. And in the gaps between these new discoveries, the black hole emerged again, this time not as a mathematical ghost but as a serious astrophysical candidate. A name that stuck. In 1967, physicist John Wheeler gave the concept a name that would capture the world's imagination: black hole. Before this, they had been called frozen stars, collapsed stars, or gravitationally completely collapsed objects. Accurate, but hardly poetic. Wheeler's phrase was simple, visual, and irresistible. A hole because once you pass its edge, you cannot return. Black because no light escapes. With a name, the black hole finally stepped into public consciousness. What had once been a half-forgotten idea now had a powerful identity. Evidence begins to speak. By the late 1960s and early 1970s, astronomers began finding more binary star systems where one star was invisible but incredibly massive. The most famous Cygnus X1 became the first widely accepted black hole candidate. Matter from its visible companion spiraled into the invisible object, heating to millions of degrees and emitting powerful X-rays before disappearing. For many scientists, this was the proof they needed. The black hole had gone from theory to observation. Why this birth was different? It's tempting to see the birth of the black hole idea as a single moment, like the flash of a star being born. But in truth, it was more like a tide rising. First the ancient myths. Then Mitchell and Laplace's thought experiments. Then Schwarzschild's radius. Chandrasekhar's limits. Oppenheimer and Snyder's collapse. And finally, Wheeler's name, joined with real astronomical evidence. Each step was slow. Each met with skepticism. But the universe is patient, and the black hole waited for us to be ready. The human side of the birth. We sometimes imagine science as a series of cold facts. But here, the birth of the black hole idea was as much an emotional journey as an intellectual one. Physicists had to learn to accept extremes, infinities, event horizons, points of no return. They had to let go of the comfort that nature might always provide a floor. The acceptance of the black hole was a deep act of humility. It was saying, the universe can be more absolute, more final, than we ever dared believe. The stage is set by the early 1970s, the black hole was no longer a whisper or a riddle. It was a recognized player in the cosmic drama. Its mathematics were clear. Its observational candidates were strong. Its name was known beyond scientific circles. And yet, we still had no way to see inside. The event horizon remained the ultimate curtain. The singularity remained a mystery wrapped in equations we could not fully trust. In our next chapter, we will follow the star itself from its birth to its final breath and see exactly how one becomes a black hole. The theory is alive. The name is fixed. Now, the cosmos will show us the process. A star's final breath. Every black hole begins its life as something radiant. It does not start as darkness. It begins as a star, a point of light in the cosmic ocean, shining across millions of years, feeding planets, giving warmth, shaping the dance of everything in its reach. Before we can understand what is inside a black hole, we must stand beside a dying star and watch how it crosses that last threshold. The long life of a giant A star is a delicate balancing act. At its heart, nuclear fusion turns lighter elements into heavier ones, hydrogen into helium, releasing vast amounts of energy. That energy pushes outward, countering the inward pull of gravity. It is this balance, outward pressure versus inward collapse, that lets a star shine steadily for millions, even billions of years. In our own sun, this balance will last about 10 billion years. But the stars that become black holes are not like the Sunday. They are giants, often 20, 30, even 100 times more massive. And like many giants, they live fast and die young. Where our sun will live for billions of years, these massive stars may burn through their fuel in only a few million. Their cores are hot, their fusion is furious, and their light can outshine thousands of smaller stars. The march toward collapse over time, the star's core changes. The hydrogen that fuels it is used up, transformed into helium. The star begins fusing helium into heavier elements: carbon, oxygen, neon, magnesium. This continues step by step, each stage faster than the last, until the core produces iron. And then, something fundamental changes. Iron cannot be fused into heavier elements without consuming more energy than it gives off. Fusion, the source of the star's outward pressure, stops in the core. For the first time in millions of years, gravity has no opponent. The catastrophe: without the pressure of fusion pushing outward, the immense weight of the star's outer layers begins to fall inward. This happens in a matter of seconds. The core collapses, its atoms crush together so violently that protons and electrons merge into neutrons. If the star is of medium-high mass, this collapse stops here, and the core becomes a neutron star, a dense sphere only about 20 kilometers across, yet heavier than the Sunday. But if the star is even more massive, above a critical limit, nothing stops the collapse. Not the resistance of neutron matter. Not the strength of atomic forces. Gravity simply keeps going. The core shrinks past the point where light can escape. The event horizon forms. And beyond it, space and time themselves are dragged inward toward a singularity. The final breath, the supernova, the outer layers of the star, falling inward, slam into the collapsing core. This rebound, combined with a flood of escaping neutrinos, triggers one of the most spectacular events in the universe, a supernova. For a brief moment, the dying star outshines an entire galaxy. It hurls its outer layers into space at thousands of kilometers per second, seeding the cosmos with heavy elements: gold, silver, uranium forged in its death throes. Planets, future stars, even life itself will one day be built from these atoms. The black hole's birth is also an act of creation. Silence falls after the supernova's flash fades, silence returns. The core has vanished behind the event horizon. There is no surface to see, no light to catch. Only the gravity remains, a silent marker of where the star once stood. From a distance, the black hole might still reveal itself by pulling in nearby gas or bending the light of background stars. But if nothing falls in, it is perfectly invisible. A star's legacy: it is tempting to think of the black hole as the end of the story. But for the universe, it is simply a transformation. The matter that formed the star has changed states entirely. Some of it has been flung into space to become part of new worlds. Some of it has crossed a threshold from which no return is possible. The black hole remains a gravitational scar in the fabric of space-time, marking where a star once burned. Different deaths. Different holes. Not all black holes are born from stars in the same way. Some are the result of direct collapse, where the star's core falls inward without even producing a supernova. Others may form in clusters of stars where massive objects merge and collapse. But in each case, the moment of creation is the same in essence: gravity wins. The structure that once held the star apart from itself gives way. Space-time folds inward, and a new kind of object, one unlike anything else, comes into being. The unreachable view: we can imagine this birth in vivid detail, but no human, no spacecraft could ever watch it from up close. The heat, the radiation, the shock waves would destroy anything in their path long before reaching the event horizon. Even if we could survive that, Time itself near the forming black hole would slow so drastically that the collapse might seem to freeze in place from our perspective. In truth, the star's final breath is not something we can witness directly. It is something we read in the light, in the ripples of space-time, in the echoes of the explosion. Why it matters to our story: we are tracing the path toward understanding what lies inside a black hole. This moment, the star's death, is the doorway. Everything that happens beyond this point is hidden behind the event horizon. The star's final breath is not just an ending, it is the moment the mystery begins in earnest. In the next chapter, we will step up to that invisible doorway. We will explore the event horizon itself, the boundary between the world we can see and the place from which nothing returns. The invisible sphere. There is a place in the universe where maps end. Where space itself stops being a stage for motion and becomes part of the fall. Where the very concept of inside and outside begins to lose meaning. That place is not a surface you can touch. It is not made of atoms. It is a boundary drawn only by the laws of physics, and it has a name: the event horizon. A sphere without a surface. Picture yourself floating in the quiet darkness of space. Ahead of you is nothing unusual at first glance, only the backdrop of stars, serene and eternal. But somewhere in that starfield lies a black hole. You can't see it directly. It emits no light. What you can see, if you're lucky, is a halo, the glow of matter spiraling toward it, heated to blinding brightness before crossing the threshold. That glowing ring marks the edge of the invisible sphere. If the black hole is perfectly still, perfectly alone, that edge is smooth and flawless, a perfect sphere. But remember, this sphere is not made of matter. It is the place in space where escape velocity, the speed you'd need to break free of gravity, reaches the speed of light. Inside this boundary, nothing can get out. Not light, not signals, not even the passage of time in any way we understand. Why event horizon? The name is beautifully literal. It is the horizon, the farthest we can ever see for any event inside it. Imagine throwing a stone into the ocean. You see the splash, the ripples. Now imagine a place where you could throw the stone, but no sound, no ripple, no sign of that throw would ever reach you. That is the event horizon, the point beyond which events stop being part of our shared universe. A one-way door. There is no physical wall here. If you were falling toward a black hole, nothing special would happen at the exact moment you crossed the horizon, at least from your own perspective. No sudden change in temperature, no jolt or bump. But from the outside, things look very different. To a distant observer, you would appear to slow down, your movements stretching into eternity as you approach the horizon. Your light would shift toward the red, fading away until you disappear entirely. From the universe's point of view, you never quite cross. From yours, the crossing happens in an instant. The shape of the horizon: in the simplest case, a non-rotating black hole, the horizon is perfectly spherical. Its size is determined entirely by the black hole's mass. For every solar mass, the radius is about 3 kilometers. That means a black hole with the mass of our Sun would have an event horizon just 6 kilometers across, small enough to fit inside a city. A supermassive black hole millions of times the Sun's mass could have a horizon spanning millions of kilometers. If the black hole spins, the story changes. Rotation drags space-time itself, flattening and twisting the horizon into a more complex shape. This frame dragging creates an even stranger region outside the horizon called the ergosphere, where space is pulled around like water in a whirlpool. No crossing back. Once something passes through the event horizon, it is cut off from the rest of the universe forever. No signal can cross outward. This is not a matter of engineering. No rocket, no technology, no clever trick can overcome it. It is a fundamental feature of the geometry of space-time itself. To escape from inside the horizon, you would have to move faster than light. And the laws of physics, at least as we know them, forbid that. Seeing the unseeable: if the event horizon is invisible, how do we see a black hole? We look for its effects. Matter spiraling toward the horizon forms an accretion disk, glowing in X-rays and visible light. Gas clouds passing nearby are heated and torn apart, their remnants stretching into arcs and streaks. Light from stars behind the black hole bends around it, producing gravitational lensing, a warped, magnified halo. In 2019, the Event Horizon Telescope collaboration captured the first direct image of a black hole's shadow, the supermassive one in the galaxy M87. What we saw was not the horizon itself, but the dark silhouette it casts against the glowing matter around it. Time at the edge. The event horizon does not only divide space. It divides time. Outside the horizon, you can move forward in time and, at least theoretically, choose your direction in space. Inside, all possible paths lead inward toward the singularity. It is not that you are pulled, it is that forward in time now points toward the center. For someone falling in, the trip from horizon to singularity would take only seconds or minutes, depending on the black hole's mass. For someone watching from outside, you would seem frozen at the horizon, stretched into infinity. The horizon as a story boundary. In our tale, the event horizon is more than a physical concept. It is the curtain beyond which the rest of the story happens in secret. It is where knowledge stops. It is where speculation, theory, and imagination take over. Crossing it, in a sense, is crossing from science into myth, because no observation can follow you there. A living edge. It is easy to think of the event horizon as static, a fixed sphere around a black hole. But horizons can grow. When the black hole swallows matter or merges with another, its mass increases, and so does the radius of its horizon. In a way, the event horizon is the black hole's living skin, expanding with each meal, shrinking, extremely slowly, if the hole loses mass through Hawking radiation. Standing on the shore. Perhaps the best way to picture the event horizon is to imagine standing on the shore of an infinite waterfall. You can watch driftwood float past you and tumble over the edge. You can even paddle, close the current stronger and stronger, but there is a line, a point, where no matter how hard you row, you cannot escape the plunge. That line is the horizon. Outside it, you can turn back. Inside it, there is only one future, down. Why the horizon matters to our journey. In our quest to know what is inside a black hole, the event horizon is the last place where the universe still lets us watch. Beyond it, there is no return signal, no data, no photograph. What lies past this edge must be built from mathematics and imagination. And yet, the horizon itself tells us something profound, that there are absolute limits in nature, boundaries not set by our technology, but by reality itself. In the next chapter, we will step across this invisible boundary, at least in thought, and imagine what it would be like to pass the one-way door to nowhere. There it is. The horizon. A perfect, silent sphere hanging in the darkness, no light, no sound, no signal escaping its embrace. You are floating just above it. There is no wall here. No shimmer, no sign that this is the edge of the known universe. But the laws of physics are clear: once you cross, there is no path back. It is a door, and it only opens one way. From the outside looking in from a safe distance, a black hole is just another massive object. Planets orbit it, light bends around it, and matter swirls toward it like leaves toward a drain. But there's a moment in your fall when you notice something subtle, a deep, growing tension between what you feel and what you see. If someone far away is watching you approach the black hole, they will see you slower, slower still, until you seem to stop entirely, frozen in place, hovering just above the event horizon. The light from your face shifts toward red, then toward black. You fade until you are invisible. To them, you never cross. You are an eternal image, hanging on the very edge. From the inside looking out from your point of view, there is no such pause. One moment, you are outside the horizon. The next, you are inside. It is not a sudden jolt. It feels like simply continuing forward, but forward is no longer what it used to be. You turn, trying to look back at the stars you came from, but the view is strange. Light from the outside universe bends and distorts. The horizon is behind you now, but it no longer looks like a boundary, it looks like a vast, glowing dome, shrinking as you fall deeper. Outside still exists, but it is receding from you in time itself. The tilt of time outside the horizon, time and space are like a stage where you can move in both directions forward in time, and in any direction in space. Inside, time tips forward toward the singularity. You cannot choose to move away from it. Every possible path, every choice of direction, leads inward. It's not that you are being pulled, it's that future now means closer to the center. If you could somehow fire a rocket pointing outward, the burn would only shorten your remaining time, because in here, outward is a direction that simply does not exist. The final journey begins. The size of the black hole determines how long this journey lasts. If it's a stellar mass black hole just a few times the sun's mass, the trip from horizon to singularity may take only a fraction of a second. You wouldn't even have time to process it before the extreme gravity tears you apart. But if it's a supermassive black hole, millions or billions of times the sun's mass, the descent could take minutes or even hours. In such a giant, the tidal forces near the horizon are gentle, you could cross without feeling much at all. Only as you near the center would those forces rise to unbearable levels. Spaghettification. Gently or violently, Stephen Hawking once described it with a smile: if you fall feet first into a black hole, the gravity at your feet will be stronger than at your head. This difference stretches you like a piece of spaghetti, a process now nicknamed spaghettification. In small black holes, this stretching happens so violently that your atoms are torn apart before you even notice the crossing. In supermassive black holes, you might pass the horizon intact, only to be pulled apart closer to the singularity. It is a reminder that black holes are not uniform. Each one has its own pace of destruction. Why no escape is possible? Let's imagine you're carrying the most powerful rocket ever built. Outside the horizon, you can fire it in any direction to slow, turn, or even escape. Inside, all those escape paths point toward the center. The geometry of space-time has changed, not as a metaphor, but as a literal fact. Your rocket is now like a swimmer in a river where the current flows faster than they can swim. Past a certain point, no matter how hard they try, the current wins. Here, the current is the flow of time itself. You can't swim upstream in time. Information lost when you cross the horizon, something else is lost: the ability of the universe to keep track of you. From the outside, no detail about what you were, your shape, your memories, your thoughts can escape. All that remains, to an external observer, is your contribution to the black hole's mass, spin, and electric charge. It is as if everything else you were is erased from the visible universe. This is what physicists call the information paradox, one of the deepest mysteries in science. If information is truly destroyed, it breaks the rules of quantum mechanics. If it is somehow preserved, we have no idea where or how it hides. A door that never closes. The one-way nature of the horizon is eternal, at least for now. Over unimaginable timescales, black holes can evaporate via Hawking radiation, shrinking and eventually disappearing. When that happens, what was once inside may, in some form we do not yet understand, return to the universe. But this is so slow that even for small black holes, it would take longer than the current age of the universe many times over. For any practical purpose, the door is permanently shut. The psychological edge: imagine actually standing, or rather floating, at the edge. The idea that there is no going back changes the way you feel about each movement. Every drift forward is a farewell to the entire cosmos. The stars you leave behind will never again be reachable. Even the light from them is now forever out of touch. You are not simply crossing space, you are crossing the boundary between participation and isolation from the rest of reality. A universe inside. Once you are inside, the outside universe becomes a shrinking light above you. You are falling toward a point that may not even be a point as we understand it. Some theories suggest the singularity may be a doorway to another universe. Others say it is simply the end, a place where all paths terminate. Some even propose that what we call inside may have its own sense of space and time, disconnected from ours. In here, speculation begins to outweigh certainty. The door as a symbol. This one-way door is not just a cosmic curiosity. It is a symbol of limits, of the places where even the universe itself says no further. It is humbling to think that, in a cosmos of trillions of stars, there are places so absolute in their isolation that nothing, no light, no hope, no information can escape. Yet it is also strangely comforting. Some secrets remain secrets, even in an age where we can see galaxies 13 billion light-years away. Looking ahead in our journey, we have crossed the horizon in thought. We have accepted that escape is impossible. Now, in the next chapter, we will begin the slow, surreal descent toward the heart, the singularity. And that will take us deeper into both physics and imagination than anywhere we have gone before. The slow descent to the singularity. You are inside now. The universe you knew, the one with stars, galaxies, and the warmth of distant light, is above you, fading. The event horizon is no longer a thing you can reach. It has become part of your past. And your future, as strange as it sounds, has only one destination, the singularity. But this fall is not always fast. The nature of down inside a black hole. Down no longer means the same thing it does outside. Outside, down is a direction in space, a vector you can point toward. Inside, down is not in space at all. It is in time. Every tick of your clock brings you closer to the singularity, not because you are being dragged in, but because the future itself lies there. You cannot stand still. You cannot hover. You are always falling, not through space, but through the very structure of reality. Two perspectives on the fall to you. The fall may feel gentle at first, especially if you've entered a supermassive black hole. No violent stretching. No sudden tearing. You float as if in deep space. But if someone outside could still see you, which they can't, not truly, they would measure your time as being hopelessly bent and compressed. They would know your story is already half over before it seems to you to have begun. In this way, the black hole plays a strange trick. It makes your own time feel smooth and ordinary, while in every other clock's language, your time is racing toward an abrupt end. Supermassive versus stellar mass descent. The difference between falling into a stellar mass black hole and a supermassive one is the difference between plunging into a waterfall and drifting down a vast, deep river. In a stellar mass black hole, only a few times heavier than our sun, tidal forces are brutal right after crossing the horizon. They stretch you atom by atom, ripping molecules apart long before you get close to the singularity. The fall is swift, violent, and terminal in less than a second. But in a supermassive black hole, the curvature of space-time near the horizon is far gentler. You might drift for hours before the forces grow dangerous. The singularity is still your fate, but it approaches with deceptive slowness. The view ahead. What do you see as you fall? Imagine a black dome below you. Not because it is a physical surface, but because that is the shape light takes when bent by such extreme curvature. The singularity itself is invisible. Instead, you see an ever-distorting pattern of the universe behind you, wrapped into a shrinking halo of light overhead. It's as if the cosmos is being drawn through the neck of a bottle, and you are already inside the narrowing glass. The sound of nothing. The silence here is different from the silence of space outside. Outside, silence is the absence of air, the absence of a medium for sound to travel. Here, silence feels heavier. It's the silence of no signal, no feedback, no connection to the rest of existence. No particle, no wave, no information makes the trip back out. You could scream, but your voice would not reach beyond your own body. You could send a message, but it would remain trapped inside the same prison as you. The black hole is not only a cage of matter, it is a cage of meaning. The slow distortion at first, your body might feel normal. Your hands still move when you tell them to. Your heartbeat still keeps its rhythm. But gradually, you notice that shapes begin to stretch subtly, almost imperceptibly. Your sense of up and down warps. Movements that once felt natural now feel tilted toward the center. This is tidal gravity at work, the tiny beginning of a force that will grow without mercy. It starts like a whisper, but you know it will end as a roar. The physics of the path: mathematically, your trajectory is called a geodesic, the straightest possible path through curved space-time. Outside, geodesics are what planets follow when they orbit a star. Inside, your geodesic points only toward the singularity. The equations are simple enough to write down, yet they carry a weight no number can soften. Your world line, the line that marks every place you ever exist in space-time, now ends abruptly in a place where space and time collapse to nothing. Falling through layers: think of this descent as passing through invisible layers. The first layer is gentle, the one just after you cross the horizon. Here, gravity feels strange but not hostile. Light still finds ways to reach your eyes from above. The next layer begins as the distortions in your view grow stronger. The halo of the outside universe shrinks, and what was once behind you begins to wrap around ahead of you, as if all directions are turning toward the same final point. By the third layer, you begin to sense that your own body is part of this bending. The atoms themselves are no longer safe. The psychological descent of black hole is as much a test of mind as it is of body. Knowing you cannot stop, turn, or send word back changes the way you think. Each moment becomes a farewell, not just to people or places, but to the concept of outside itself. You begin to wonder whether the singularity is truly the end, or if it is a kind of passage. Some part of you hopes, and another part accepts that this may be the last hope you ever feel. The river model: physicists sometimes describe black holes as rivers of space flowing inward faster than the speed of light. Outside the horizon, you can paddle against the current and escape. Inside, the current is faster than any possible speed you can reach. In this model, the singularity is not a place you are pulled to, it's the waterfall at the end of the river. The horizon is simply where the water's speed overtakes your ability to resist. From here on, the current only grows stronger. The inescapable clock: every black hole has a proper time, the amount of time, measured by your own clock, from horizon to singularity. For some, that time is less than a second. For others, it is hours. But no matter how large the black hole is, that clock always runs out. There is no drift, no orbit, no clever maneuver that can prolong it beyond its limit. This is the truest sense in which black holes are traps. They are not just prisons in space, but in time itself. Approaching the point of no physics: as you draw closer, the known laws of physics begin to falter. Einstein's equations predict infinite density, infinite curvature, a place where our mathematics simply breaks. Physicists suspect that something else must happen here. Perhaps quantum gravity, a theory uniting general relativity and quantum mechanics, would smooth out the infinities. Perhaps the singularity is not a point, but a region where space-time transforms into something utterly alien. But from here, theory offers only shadows. The truth lies ahead, and no one has ever come back to tell it. The final calm: there may come a strange moment, just before the tidal forces overwhelm you, when everything feels still again. The distortions in your vision are now absolute. The outside universe is gone from view. In this instant, you are suspended in a silence that feels infinite. There is no horizon anymore, only the deep, invisible slope toward the end of your path. You are as close to the singularity as you will ever be aware of being. After this, there is only the unknown. In the next part, we will leave this slow fall and arrive at the heart of the black hole, a place where our understanding of space, time, and reality itself is tested to its breaking point. Meeting the singularity, you have been falling for what feels like both forever, and no time at all. Above you, the light of the outside universe has already folded into darkness. Around you, there is no around, only a strange, relentless pull towards something you cannot see. And then, without warning, the singularity is no longer ahead of you. It is everywhere. A place that isn't a place: we call it a point, but that is only a human word for something that cannot be drawn, measured, or even properly imagined. A point has coordinates. A singularity does not. It is the end of coordinates, the end of distances, the end of here and there. It is the moment when the fabric of space-time, stretched and curved by gravity beyond all limits, folds entirely in on itself. From the outside, it is an abstraction, a mathematical conclusion that emerges from Einstein's equations. From the inside, it is the inevitable final page of your personal timeline. The physics on paper, Einstein's general relativity, says that the singularity is where curvature becomes infinite. That means the bending of space-time is so extreme that all known physical laws break down. Imagine drawing a circle smaller and smaller, never quite reaching zero size. Now imagine that instead of a flat line, you are shrinking an entire 3D reality. At the singularity, that shrinking has no limit. Physicists write it as a limit in their equations. The numbers climb toward infinity. And infinity is not just very big. In physics, infinity is where the map stops, where the equations tell you. Beyond this point, I cannot speak. What you would experience, here's the strange part: if you are falling toward the singularity inside a supermassive black hole, you might not feel a sudden, violent impact. Instead, the tidal forces, the stretching of space between your head and your feet, would increase until they tear you apart, molecule by molecule, atom by atom. This disassembly is not something you could resist. No material, no matter how strong, can survive infinite curvature. In the case of a stellar mass black hole, this destruction happens well before you reach the singularity. In a supermassive one, you might reach it still in one piece, though the meaning of piece becomes murky here, because your concept of a location no longer applies. A singularity is not just the center. It's tempting to imagine the singularity as a hard ball sitting at the middle of the black hole, waiting for you like a pearl inside a shell. But that picture is wrong. The singularity is not in space. It is in time. When you fall in, you are not moving toward it the way you would move toward a planet's surface. You are moving toward it the way you move toward tomorrow. It is simply the next moment in your future. Inside the event horizon, all possible futures end here. You cannot choose to go elsewhere any more than you can choose to step outside of time. The wall of no return, in a way, the singularity is the ultimate now. It's the point in your personal journey where every line of your existence, your body, your thoughts, your particles, converges to zero. If space-time were a sheet of paper, the singularity is the place where all the folds meet in one impossibly tight crease. Once you are in that crease, there is no more paper left to walk on. The quantum mystery, Einstein's theory, takes us right up to the singularity, and then stops. It cannot tell us what is inside. But physicists suspect that quantum mechanics, the theory that governs the very small, might soften the infinities, replacing them with something finite but strange. Some suggest that the singularity could be a dense knot of quantum fields. Others imagine it as a Planck scale region, where space and time themselves are granular, made of indivisible units. And then there are the more daring possibilities, that the singularity is a doorway to another universe. That what falls in might re-emerge somewhere else in space-time. That the information swallowed is somehow preserved in a form we do not yet understand. These ideas live in the territory where science and speculation brush against each other like shadows. The inside-out view from your own perspective: if you could remain conscious and whole right up to the singularity, you would never see yourself reach it. Instead, your perception of time would break down before you could witness the final instant. It is not that you would black out in the ordinary sense. It's that before and after would lose meaning. There would be no sequence to follow, no moments to measure. To an outside observer, if such an observer could exist, your entire fall would be finished in a finite amount of your own time, even though from their distant view you were frozen at the horizon. The roll of light, inside a black hole, has only one path: down. Just like you. It cannot stand still, cannot escape, cannot bounce from wall to give you an image of your surroundings. This is why the singularity is not visible, not even as a shadow. It is the absence of light's ability to tell a story. You do not see the singularity. You feel its inevitability. What happens to matter as you approach? Matter ceases to be matter in any familiar form. The concept of solid is erased. Atoms are stripped into subatomic particles, and even these particles are smeared into pure energy by the tidal forces. At this point, your original form, the one that once walked on a planet, saw sunsets, and wondered about the stars, is gone. What remains is a trace of mass energy, still following the space-time path to its end. It is not death in the biological sense. It is the dissolution of physical identity. Why it still matters, you might wonder. If no one can survive to see the singularity and tell us about it, why does it matter? It matters because the singularity is not just the end of objects, it is the end of our current understanding of the universe. It is the place where the most powerful theories of the 20th century, general relativity and quantum mechanics, both fail to give a complete answer. And wherever answers fail, new truths may wait. A possible escape, in theory. Some speculative models, wormholes, white holes, quantum bounce cosmologies, suggest that the singularity could lead somewhere else. Perhaps what falls in is not destroyed, but transformed. Perhaps the crunch at the center is actually the seed of expansion somewhere else. These are poetic possibilities, and until we have a theory of quantum gravity, they remain only that, possibilities. Still, even possibilities can inspire. The final moment, what is it like, the last instant? No one knows. It may be that consciousness cannot bridge the gap. That the final transition is beyond the reach of awareness. But if it could, perhaps it would feel like everything past, present, and future collapsing into one single, infinite point. No boundaries, no distances, no time between moments. Only a kind of absolute presence, and then, nothing. The singularity as a question. In truth, the singularity is less of an answer and more of a question with teeth. It asks us, what happens when our laws of physics are pushed to their breaking point? It reminds us that even the most confident equations have their blind spots. And maybe, it whispers to us that what we call the end might also be the beginning of something we have no words for yet. In the next chapter, we will step back, not physically, for there is no stepping back from here, but in thought. We will explore what the singularity means for the universe as a whole, and why black holes, instead of being cosmic destroyers, might actually be part of its deep creative machinery. The singularity's role in the universe. You might imagine the singularity as a lonely, silent thing. A hidden heart of darkness, sitting forever at the center of its black hole. Alone. Forgotten. Unreachable. But the universe rarely wastes anything. Even its most mysterious creations seem to have their place in a greater pattern. And the singularity, this extreme point where our physics gives way, may be far more than a cosmic dead end. From the edge to the center we began our journey at the event horizon, the black hole's outer boundary, the point of no return. We crossed through space-time like travelers on a one-way path, drawn ever deeper by gravity's insistence. We watched light itself fall, unable to turn back. And now, in our imagination, we are standing, or rather being, at the singularity, the very center of the black hole's story. From here, we can only look outward with our minds, for our senses have no grip on the scene. So let's step back in thought, and ask, what is this place doing for the universe? The end that shapes the beginning. To many scientists, the singularity is a boundary, a place where calculations end. But it might also be a generator. Consider this: our own universe may have started as something very much like a singularity. The Big Bang, at least in its earliest moments, is described in some models as a singularity: infinite density, infinite temperature, zero size. If that is true, then singularities are not just destructive. They can be creative. They can be the seed from which entire universes bloom. A black hole as a cosmic recycle point. When a star dies and collapses into a black hole, its matter and energy are not erased from existence. They are taken in, compressed, hidden from view, but they still exist. Some speculative theories, like loop quantum cosmology, suggest that instead of matter being crushed into nothingness, it might reach a point of maximum density and then bounce emerging elsewhere or else when in a form of expansion. If this is so, then black holes might be part of a recycling system. Stars burn their fuel, collapse into black holes, feed their singularities, and those singularities might seed new regions of space-time. The cycle would be strange, invisible, and perhaps endless. Galactic architects. Here's another clue: many, perhaps all, large galaxies including our own Milky Way seem to have a supermassive black hole at their center. Astronomers believe these giants may play a role in organizing the galaxy itself. The intense gravitational influence of a central black hole could shape the orbits of billions of stars, help gather matter into spiral arms, and influence how new stars form. If that's true, then singularities are not just hidden curiosities, they are part of the scaffolding of the cosmos. They help hold the grand design in place. Energy in disguise from outside the event horizon. The singularity's presence is invisible, but the black hole it creates can be one of the brightest objects in the universe. When matter falls toward the singularity, it often forms a hot, swirling disk, an accretion disk. Friction in this disk releases enormous amounts of energy, sometimes blasting out in jets that stretch thousands of light years. Quasars, the brilliant beacons we can see from across the cosmos, are powered by supermassive black holes feeding on infalling matter. In a way, the singularity is at the heart of these light shows, fueling them from behind the curtain. The singularities that feed growth. Some simulations suggest that early in the universe's life, black holes grew quickly, swallowing matter and merging with each other. Their gravitational pull may have helped gather raw material for the first galaxies. Without these early singularities, the universe might have been a far emptier place. No great spirals of stars. No heavy elements forged in supernovae. Perhaps no Earth. Perhaps no us. An unseen balancer. Black holes also act as a kind of cosmic regulator. Too much matter in a region, and the gravitational collapse into black holes can redistribute energy and slow star formation. Too little, and the balance shifts again. The singularity is the hidden center of this balancing act, not directly controlling it, but existing as the inevitable outcome of certain conditions. In this way, singularities are like silent bookends, one at the start of a star's life, in the collapsing cloud that births it, and one at the end, in the collapse that takes it back. Are we living in a black hole? There's a mind-bending idea in theoretical physics: what if our universe itself is the inside of a black hole, born from the singularity of another universe? The reasoning comes from how space-time curves inside a black hole. From the outside, it looks like matter is falling in toward a central point. From the inside, that central point could look like an expanding space, a new cosmos. If true, then every singularity could be a womb for a universe. And our own Big Bang might simply be the other side of some parent black hole's collapse. The information puzzle. The singularity is also at the heart of one of the most famous paradoxes in physics: what happens to information that falls into a black hole? Quantum mechanics insists that information, the complete description of a system state, cannot be destroyed. General relativity seems to allow it to vanish into the singularity. This conflict is not just academic. It's a sign that our understanding of reality is incomplete. And the resolution to this paradox could reshape our view of everything from quantum computing to the birth of the universe. Some recent work hints that information may be preserved in subtle ways, encoded on the event horizon in a holographic form. If so, then the singularity is not a shredder, but a vault. A teacher by mystery. In a strange way, the singularity's greatest role in the universe might be as a teacher. It shows us where our current knowledge stops. It invites us, forces us to imagine new frameworks. When Newton's laws could not explain Mercury's orbit, we found Einstein's relativity. When relativity and quantum mechanics both fail at the singularity, we know something even deeper must wait beyond. And so the singularity stands not just as an object, but as a question carved into the structure of space-time itself. The poetry of role. You could say the singularity's role is twofold. In the physical universe, it shapes galaxies, recycles matter, and perhaps seeds new worlds. In the mental universe, the universe of human thought, it draws us onward, toward greater understanding. It is both a hidden engine and a riddle. Both a heart and a horizon. From death to creation, a star dies. Its core collapses. The singularity is born. And yet, in the wider picture, this is not just an ending. The star's light may have seeded life on distant worlds. Its collapse may have forged heavy elements that will form new planets. Its singularity may influence the birth of whole galaxies. The universe speaks in cycles, not straight lines. The singularity is one of its punctuation marks, a period that is also a comma. Our place in the pattern. When you look up at the night sky, you are not just seeing stars. You are seeing the work of singularities across billions of years. Some of those points of light are in galaxies whose centers hide supermassive black holes. Some of those galaxies may not exist without them. And without galaxies, there might be no stable environments for life to arise. In this way, the singularity's role touches even the quiet breath you take right now. Why the role matters to us. It might seem distant, these invisible, unreachable points deep in the fabric of space. But their existence shapes the large-scale universe in which our small-scale lives unfold. Understanding them is not just about curiosity. It's about understanding the forces that shape the conditions for our own existence. Looking ahead, the singularity's role is not fixed in stone. Our theories may change it entirely. One day, a theory of quantum gravity may reveal that what we call a singularity is something richer, stranger, and even more beautiful. Until then, it stands as one of the universe's most eloquent silences. In our next chapter, we will drift even farther outward to see how black holes, with their hidden singularities, shape the grand structure and fate of the cosmos itself. Black holes and the shape of the universe. When you look up at the night sky, you might think of it as an endless spread of stars. Bright dots scattered randomly across a black canvas. But the universe has shape. It has a structure, a pattern, and a kind of cosmic architecture built not by hands, but by forces older than time itself. And hidden among those forces, are black holes. The silent sculptors. Black holes are not just isolated traps for matter and light. They are sculptors. They pull. They bend. They guide the dance of stars and gas over billions of years. From the smallest stellar mass black holes to the gargantuan supermassive ones in galactic centers, their gravity works silently but persistently. Like invisible anchors, they hold the delicate curves of galaxies together, or sometimes, they tear them apart. If you could stand outside the universe and look down upon it, you might see its great filaments of galaxies stretched across the void. And deep inside those threads, in many of the bright knots where galaxies cluster, you would find black holes at work. Galactic centers. The black hole's domain. Our own galaxy, the Milky Way, has a heart, a supermassive black hole called Sagittarius A star. It is about 4 million times the mass of the Sunday. To the casual observer, it is invisible. But astronomers have tracked the orbits of stars whipping around it, moving so fast that only an immense gravitational pull could hold them. These central black holes do not just sit idly. When they are actively feeding on matter, their influence can extend far beyond their immediate reach. Jets of high-energy particles can blast out from their poles, cutting through interstellar space like cosmic searchlights. These outflows can heat gas clouds and stop them from forming new stars, a process called feedback. In this way, black holes can regulate the growth of their galaxies, controlling the birth rate of stars like gardeners pruning a tree. The cosmic web. On the largest scale, the universe looks like a vast web. Galaxies are strung along thin threads of dark matter, clustered together at intersections called nodes. Black holes may influence this grand pattern in subtle ways. When galaxies merge, a common event in cosmic history, their central black holes often spiral toward each other and eventually merge too. The release of gravitational waves in these events can ripple through surrounding matter, redistributing energy and momentum. In the long run, these mergers help determine the size and shape of galactic clusters, which are the building blocks of the cosmic web. Shaping through destruction, it might seem strange that something known for destroying matter could be a builder of structure. But destruction in the cosmos often leads to creation. When a massive star collapses into a black hole, it can trigger supernova explosions that enrich the surrounding space with heavy elements, the very materials needed for planets and life. These explosions can also send shock waves that compress nearby gas clouds, triggering the formation of new stars. So, even the birth of a black hole can reshape its local environment in profound ways. Black holes as galactic regulators. Supermassive black holes act like thermostats for galaxies. If too much cold gas accumulates in the center, a feeding frenzy begins. The black hole consumes matter rapidly, releasing vast amounts of energy. This energy can blow away or heat up the remaining gas, slowing star formation for millions of years. Without this self-regulating process, galaxies might burn through their star-making fuel too quickly, leaving them barren and dim in the later ages of the universe. The early universe and black hole growth. When the universe was young, less than a billion years old, it already hosted black holes with masses billions of times that of the Sun. How did they grow so quickly? One possibility is that the first generation of stars, made almost entirely of hydrogen and helium, were enormous. When they died, they left behind massive black holes that could feed and grow rapidly. Another possibility is direct collapse, enormous clouds of gas collapsing straight into black holes without first forming stars. Whatever the mechanism, these early giants may have been the seeds from which today's largest galaxies grew. Shaping space-time itself. Einstein's general relativity tells us that mass and energy shape the very fabric of space-time. Black holes, with their extreme densities, curve space-time more intensely than anything else we know. In a sense, black holes are local distortions in the geometry of the universe, deep wells in the cosmic landscape. As they move, merge, or interact, they send ripples through this landscape, gravitational waves. In 2015, LIGO detected such waves from the merger of two stellar mass black holes. This was more than just a triumph of technology, it was proof that black holes can send their influence across billions of light-years, subtly shaping the dynamics of the cosmos. The fate of the universe and black holes. Black holes also figure into the question of how the universe will end. If the universe expands forever, stars will eventually burn out, galaxies will fade, and black holes will become the last strongholds of matter. Over unimaginable timescales, even they will slowly evaporate through Hawking radiation, releasing their energy back into the universe. In that far future, the shape of the cosmos will be set not by the clustering of galaxies, but by the slow, graceful fate of these dark giants. A universe without black holes? It's worth imagining a universe without black holes. Would galaxies still form? Probably, but their structure might be looser, their centers less organized. Star formation might proceed unchecked, exhausting resources too soon. The balance between creation and destruction might tip toward chaos. In this sense, black holes may be one of the quiet stabilizers of the universe's architecture. Black holes as storytellers of cosmic history. Every black hole carries a record of the events that created it: a stellar collapse, a merger between galaxies, a feeding episode where matter spiraled inward in luminous streams. By studying their masses, spins, and environments, astronomers can piece together the story of cosmic evolution. They are not just shaping the universe, they are also its memory keepers. Invisible but indispensable. The irony of black holes is that they are invisible by nature, yet they may be indispensable to the universe's visible beauty. The spiral arms of galaxies, the balance of star birth and death, the very rhythm of cosmic time, all may owe something to their influence. The poetry of shape. If you were to paint the universe, you would use strokes of light for stars and galaxies, but the hidden shapes, the skeleton beneath the paint, would be drawn by gravity. And in the deepest, most decisive lines, you would find the work of black holes. They are the silent punctuation marks in the sentence of creation. They give the story its pauses, its climaxes, its endings, and perhaps, its beginnings again. In the next chapter, we will travel even farther into speculation to ask, could black holes be gateways to other universes, and if so, what would that mean for the shape of reality itself? Black holes as gateways to other universes. There is a certain kind of question that only blooms in the quiet hours. The kind that asks, what if? Not what is, but what could be. And tonight, we will let ourselves wander there. Past the borders of known science. Into the shimmering territory where theory, imagination, and wonder intertwine. What if a black hole wasn't only an end? What if, beyond its darkness, there was, somewhere else? The seed of the idea for most of human history, a black hole was thought of as a dead end. A place where matter goes to vanish, light goes to die, and time itself loses meaning. But physics, when pushed to its extremes, has a way of opening secret doors. Einstein's equations of general relativity don't only allow for black holes. They also allow for their mirror image, white holes. A white hole is a hypothetical object that does the opposite of a black hole. It throws matter out instead of swallowing it in. No one has ever seen one, but mathematically, they could exist. And this led to a startling thought: what if the inside of a black hole was connected to a white hole, in another universe? The wormhole connection. A wormhole is a theoretical bridge through space-time. Imagine the fabric of the universe as a sheet of paper. If you fold the paper so that 2 points touch, and then pierce through, you create a shortcut between distant places. Some solutions to Einstein's equation suggest that a black hole could be one end of such a tunnel, with a white hole at the other end, spilling out matter into a different part of the universe or even into a completely separate universe. In these scenarios, the black hole's crushing gravity is not the end of the road. It's the doorway. A birthplace for new universes. Some physicists have proposed that the Big Bang itself could have been the white hole end of a wormhole, connected to a black hole in another universe. It's an idea almost too vast to grasp, that every black hole in our cosmos might contain the seed of a new universe inside it. And that our own universe might be nestled inside the black hole of some greater, older cosmos. This is sometimes called the cosmological natural selection theory. In it, universes reproduce through black holes, and those universes whose laws of physics favor black hole formation produce offspring more efficiently. In such a scenario, black holes are not just destroyers, they are cosmic wombs. The physics problem. The trouble is, our current understanding of physics falters when we try to peek beyond a black hole's event horizon. Inside, gravity grows so intense that quantum mechanics and general relativity, the two pillars of modern physics, no longer agree. We need a theory of quantum gravity to truly know what happens there. Until then, all talk of other universes remains speculation, however beautiful. The white hole's stranger traits. If a black hole is perfectly black, a white hole would be perfectly bright, radiating matter and light, but impossible to enter. It's an idea that makes for poetic symmetry, but also raises puzzles. Where would all that matter come from? If it came from our black hole, how would it escape the singularity, the point of infinite density at the black hole's center? One possible answer: perhaps there is no singularity at all. Perhaps the core of a black hole is instead a tiny, dense region where space-time bounces, reversing the collapse and expanding into another realm. Einstein-Rosen bridges. In 1935, Albert Einstein and Nathan Rosen described what we now call an Einstein-Rosen bridge, a theoretical connection between two regions of space-time. In their original interpretation, this bridge connected a black hole to a white hole. The bridge, however, was unstable. Anything trying to pass through would cause it to collapse before it could cross. Later work in quantum physics introduced the idea that exotic forms of matter, with negative energy, might stabilize such a tunnel. This exotic matter has never been observed, but in principle, it could keep a wormhole open long enough for something or someone to pass through. What would it be like to fall through? Imagine drifting toward a black hole. The stars behind you stretch and bend in strange ways. Time seems to slow. Your heartbeat echoes louder in your ears as the event horizon approaches. In our universe, once you cross that invisible boundary, no signal can return. But if the wormhole scenario is true, you might instead find yourself passing through a narrow, twisting throat of warped space-time. Light from the other side could shine in strange colors. Gravity might shift direction. And then, perhaps suddenly, you would emerge. Not into a void, but into a blazing, expanding space, a newborn universe. Why this matters? Even if it's not true whether or not black holes are actually gateways, thinking about them this way stretches our imagination. It pushes science toward new questions. It reminds us that the universe might be more connected, more layered than we suspect. In many ways, science advances by chasing such what-if questions, even if most turn out not to match reality. Sometimes, the path they lead us down reveals discoveries we could never have reached otherwise. A poetic parallel: black holes as portals mirror the human experience in a way. Sometimes in life, it feels like we've reached an ending, a collapse. And yet, in that darkness, a new beginning may be forming, unseen. The thought that every end might also be a beginning, whether in life, in nature, or in the very fabric of the cosmos, is a deeply comforting one. The limits of our vision for now: telescopes can only see the shadows black holes cast, and the matter swirling just outside their event horizons. We cannot peer inside. We cannot confirm if there is another universe beyond. But this limitation is not a failure, it is a horizon of its own, a place where curiosity gathers like clouds before a storm, waiting for the lightning of understanding. Future paths: as gravitational wave astronomy improves, as quantum theory and relativity inch closer together, and as computer simulations grow more powerful, we may begin to see hints, indirect signs of whether wormholes and white holes are more than just beautiful mathematics. Until then, the idea will remain suspended between science and dream, a shimmering maybe in the dark. And so, as you drift toward sleep tonight, imagine the black holes in the sky above you, not as hungry ends, but as mysterious doorways. Doorways that may open not just into other corners of our cosmos, but into entirely new realities. After all, the universe is not obligated to be limited by our current understanding. And sometimes, the truth waits for us far beyond the edge of what we can see. In our next chapter, we will turn from portals to paradoxes, and explore topic 13: the black hole information puzzle. Can anything truly be lost? The black hole information puzzle: can anything truly be lost? There is a certain chill in thinking about black holes. Not just because they are dark and silent, but because, for decades, they carried with them a question that seemed to cut to the heart of reality itself: if something falls into a black hole, is it gone forever? This is the black hole information paradox. And it is one of the most haunting mysteries in all of physics. The stage is set. First, let's rewind the scene. A black hole forms. A star collapses, matter falls inward, and gravity locks everything behind the event horizon, that invisible border from which nothing, not even light, can return. From the outside, all you can see is the black hole's shadow and the halo of light from matter spiraling into it. Once an object crosses the horizon, its details seem to vanish. In everyday life, things change shape, burn, or crumble, but information about them is still, in theory, preserved. A burnt letter still leaves behind ashes and smoke molecules. In principle, you could reconstruct its content from those fragments if you had godlike precision. But with black holes, this seemed impossible. The event horizon appeared to erase all trace of an object's original properties. Hawking's shocking discovery in the early 1970s. Stephen Hawking was studying quantum effects around black holes. He discovered something astonishing: black holes are not perfectly black. Due to quantum fluctuations at the event horizon, pairs of particles constantly pop in and out of existence. Sometimes, one falls in while the other escapes. The escaping particle carries away a tiny bit of the black hole's mass and energy. This process is now called Hawking radiation. Over unimaginably long time scales, this radiation would cause the black hole to slowly shrink and eventually evaporate completely. At first, this was thrilling: black holes weren't eternal. But then came the troubling question. The disappearing act. If a black hole evaporates away, what happens to the information about what fell in? Where does the record of that matter's properties go? If Hawking radiation contains no imprint of the infalling material, if it is purely random, then the information is gone, lost from the universe. And that would break the rules. The laws of physics say no. In quantum mechanics, there is a principle called unitarity. It says that the evolution of the universe is reversible. If you know the present state perfectly, you can, in theory, reconstruct the past. If black holes destroy information, unitarity is broken. And if unitarity is broken, the whole foundation of quantum theory begins to crumble. This is why Hawking's early conclusion that information was lost sent shockwaves through the physics world. The great debate for decades, physicists were divided into camps. The information is lost camp, led by Hawking and others early on, argued that black holes fundamentally erase the past. The information is preserved camp insisted that somehow, someway, the universe keeps its books balanced. The debate was fierce, spanning conferences, papers, and late-night arguments in chalk-dusted rooms. Possible escape routes for information. If information can't simply vanish, how might it escape a black hole? It's stored in the Hawking radiation. Some proposed that Hawking radiation is not truly random. It might carry subtle correlations encoding the lost information. This would mean the radiation, over time, releases the record of everything that fell in, scrambled but retrievable. It's stored on the event horizon. In the 1990s, the holographic principle emerged: the idea that all the information inside a black hole is encoded like a hologram on its surface, the event horizon. If true, this would mean nothing inside is truly lost. The information is painted on the black hole's boundary. It escapes through wormholes. More speculative ideas suggest that information might exit through hidden tunnels in space-time, possibly even into other universes. Firewalls. A more dramatic proposal, the firewall hypothesis, suggested that the event horizon might be a wall of high-energy particles that burns up anything crossing, releasing its information before it truly enters. But this clashes with the idea that falling into a black hole should be uneventful at the horizon for large black holes, the no-drama principle. Hawking's change of heart. In 2004, Hawking surprised the world. He announced he had changed his mind: information is preserved. He proposed that it might be stored in a subtle, complex way in the Hawking radiation, so complex that for all practical purposes, it's unrecoverable, but not truly gone. It was a humbling and human moment in science, a great mind revising his stance in the face of new reasoning. Why it matters beyond black holes. This puzzle is not just about distant, exotic objects. It's about whether the universe plays fair with its own rules. If information can be destroyed, then predictability and consistency in physics collapse. It would mean that the past could be forever erased, not just hidden. But if information is always preserved, then even in the heart of a black hole, there is a kind of cosmic bookkeeping. A promise that nothing is ever truly lost. The holographic universe. The holographic principle, born partly from studying black holes, has grown into a profound idea: the entire universe might be like a hologram, where the 3D reality we experience is encoded on a distant 2D surface. In this view, a black hole is a local example of a much bigger truth. The inside is an illusion, everything is really stored on the outside. It is a mind-bending, poetic vision that reality itself might be woven in the same way that a black hole preserves its secrets. Recent clues. In recent years, advances in string theory, quantum gravity, and studies of entanglement have provided models showing how Hawking radiation could gradually leak information out. Calculations of page curves graphs predicting how information might be released over time match these models, hinting that the paradox might finally be resolving in favor of preservation. But these are still theoretical clues, not experimental proof. Black holes are too distant, too subtle, for us to yet read their messages directly. A meditation on loss. In the end, the black hole information paradox is as much a philosophical question as it is a scientific one. It asks us whether the universe forgets, or whether it remembers everything. There's a certain comfort in believing that nothing is ever truly gone. That even if scattered, transformed, or hidden beyond light, the story remains somewhere, somehow. Maybe, just maybe, the same is true for our own lives. Our choices, our moments, our presence all etched into the vast memory of existence. The road ahead, the paradox, is not yet fully solved. But the journey toward the answer has already reshaped our understanding of space, time, and reality. And so, as you drift toward sleep, imagine the universe as a patient librarian. Every particle, every whisper of energy, every star that ever was catalogued, cross-referenced, never truly lost. Even in the darkness of a black hole, the story endures. In our next chapter, we will step into the most mysterious chamber of all. Inside the event horizon, a one-way journey to the singularity, there is a line in space, invisible, silent, without color or shimmer. Yet it is the most final border in the known universe. It is called the event horizon. Cross it, and there is no turning back. Not for you. Not for light. Not for any whisper or signal that might tell the outside world what has become of you. And beyond that line, the road leads only one way, toward the singularity. The moment of crossing, imagine you are floating toward a black hole, gently at first. From far away, it is nothing more than a dark disk against the background of stars, encircled by a glowing halo of light matter spiraling in at furious speeds. But as you approach, the pull strengthens. Gravity deepens its hold on you, not like the sudden jerk of a fall on Earth, but like an invisible tide, constant and irresistible. Time seems normal to you. Your heartbeat still feels steady. But if someone far away were watching, they would see you slow down. Slower. And slower still, until, at the edge, you appear frozen. Your image would fade, stretched and reddened by the gravitational pull, until you disappear entirely from their view. For them, you never truly cross the horizon. For you, you pass through in an instant. No drama, or is there? In the classical view of black holes, you wouldn't notice anything unusual as you crossed the event horizon, at least if the black hole were large enough. No sudden shock. No flash of light. Just the stars behind you, now forever hidden from sight. The horizon is not a physical wall, it is a boundary in space-time, marking the limit of escape. But modern theories have begun to question whether there might, in fact, be something dramatic, perhaps even violent, at this edge. Some physicists imagine a firewall, a region of intense energy that would incinerate anything attempting to cross. Others believe this is unlikely, and that the old no-drama principle still holds. For now, the truth remains hidden behind the veil. A new direction for time. Once inside the event horizon, the very nature of movement changes. Outside, you can choose where to go: forward, backward, sideways. Inside, all paths point inward. It's as if toward the singularity has become your new forward in time. No matter how hard you try to resist, no matter what engines or wings you might have, moving away from the center would be like trying to move backward in time. Impossible. The stretching of space and the stretching of you as you fall inward, tidal forces begin to grow. If you were heading into a small black hole, these forces would be extreme even before crossing the horizon. Your feet would feel a stronger pull than your head. This difference would stretch you, molecule by molecule, atom by atom, until you were a long, thin thread of matter. Physicists have a whimsical name for this: spaghettification. In a supermassive black hole, though, you could cross the horizon without feeling much at first. Only as you drew nearer to the singularity would the stretching begin to intensify. The view from within looking out, you would see the universe shrink into a small, bright patch of sky, the last light from the outside world. But that patch would be distorted. The black hole's curved space would twist and stretch the view until directions lost their meaning. Photons, particles of light, would follow bent paths, circling the singularity or spiraling in alongside you. Some would seem to come from impossible angles, wrapping the universe into strange shapes before your eyes. It would be beautiful and terrifying. The approach to the singularity in the center, hidden in perfect darkness, lies the singularity, the point where all the black hole's mass is concentrated. Here, our understanding of physics breaks down. General relativity predicts infinite density, infinite curvature of space-time. Quantum mechanics rebels at such infinities, suggesting that our theories are incomplete. What truly exists at the core? A point? A tangled knot of space-time? A bridge to another universe? No one knows. But for you, falling inward, the journey ends there, not in a sudden crash, but in the inevitable convergence of all paths, all timelines, all possibilities into one final instant. The end of the story or the beginning of another. From the outside, your fate is sealed the moment you cross the event horizon. From your perspective, your fall is swift, perhaps seconds in a small black hole, hours in a supermassive one. What happens beyond that final instant remains a mystery written in the mathematics of a theory we have yet to complete. Some dream that inside the singularity lies the seed of a new universe, a bubble of space-time budding off from our own. Others imagine that the singularity is not a thing but a doorway, a place where the familiar fabric of reality gives way to something entirely different. A gentle reflection inside the event horizon: there is no going back. It is a place where direction, distance, and time are reshaped into something unrecognizable. And perhaps that is why the thought of it captures us. It is a metaphor for moments in life when there is no return, when we are carried forward into the unknown. As you drift toward sleep, picture yourself passing through that silent boundary, feeling the universe change its rules around you, and letting go, floating onward into the most hidden chamber of the cosmos. In our next chapter, we will step even closer into the very heart of the black hole itself. The singularity, where space-time ends and mystery begins. There is a place in the universe where all our maps fail, where equations we trust begin to tremble, where the very concepts of before and after, here and there, dissolve into something strange and untethered. That place is the singularity of a black hole. It sits at the heart of the darkness, the center toward which every path inside the event horizon leads. Not a physical object in the way we think of stars or planets, but rather, a point in space-time where gravity becomes infinite. Or so our current theories tell us. A word that means we don't know. The word singularity sounds precise, even sharp. But in truth, it is more like a label we place over a mystery. Mathematically, in Einstein's general relativity, the singularity is a solution where the curvature of space-time becomes infinite and all matter is compressed into an infinitely small point. It is a place where density is beyond measure, and the rules we use to describe the universe no longer apply. Physicists sometimes joke that singularity is just code for our math has broken down here. And in a way, it's true. It's not that nature wants infinities, it's that our current models cannot yet tell us what actually happens at such extremes. Following the river to its source inside the event horizon, every path you take is a path toward the singularity. It doesn't matter if you're moving forward or backward in the way you think of on Earth, here. Forward in time simply means closer to the center. It's like being caught in a river where the current flows only one way. You can spin or swirl, you can fight the water, but the destination is inevitable. And as you draw near, the forces at work grow stronger than anything else in the universe. The collapse of meaning. Imagine you had a clock with you, ticking steadily in your hand. To you, it works fine, tick, tick, tick. But as you approach the singularity, those ticks bring you closer to a moment where the clock, and you, and the very concept of ticking, can no longer exist. Length and width lose meaning. Even the distinction between past and future may vanish. Space-time itself curves inward so sharply that our minds evolved to handle the gentle slopes of planets and the soft arcs of starlight can barely imagine it. A place of all histories. Some theories suggest that the singularity is not just a point in space, but a point in time. From this view, the singularity is the future of everything inside the black hole. It's not somewhere you go, it's something you become. Once inside, every path you take through space is also a path through time, and all of them lead to that same ultimate moment. In this sense, the singularity could be thought of as the final page of a book, different characters, different journeys, but all ending in the same last line. The quantum rebellion. General relativity leads us here, to infinities and impossibilities. But quantum mechanics, the other great pillar of modern physics, refuses to play along. Quantum theory tells us that nothing can be measured to infinite precision, that uncertainty and fluctuation are woven into the fabric of reality. It suggests that perhaps the singularity is not a point of infinite density, but rather a place where the smooth surface of space-time breaks into something granular, foamy, or tangled. Physicists call this yet unknown theory of gravity and quantum mechanics together quantum gravity. And until we have it, the singularity will remain a locked room we cannot fully enter. A seed for new worlds. One of the most beautiful and speculative ideas in cosmology is that the singularity of a black hole might not be an end at all, but a beginning. Some researchers imagine that what we call a singularity is actually a bridge to another region of space-time, perhaps even the birth of a new universe. A white hole could exist on the other side, a region that only emits matter and never takes any in. In this picture, black holes could be cosmic wombs, quietly giving birth to universes hidden from our own, each with its own laws of physics. It's a poetic idea, but as of now, it lives in the realm of mathematical possibility, not proof. The inescapable truth. Even without knowing exactly what lies at the singularity, one truth stands firm: no signal, no light, no story from within will ever escape to tell us. For anyone or anything falling inside, the singularity is both the final destination and the end of their timeline. The universe beyond will never know what they experienced in their last moments. This silence is part of the black hole's power. It is a mystery wrapped not just in darkness, but in perfect isolation. What it means for us, though we may never stand at the singularity, the concept changes how we see reality itself. It shows us that our theories, as powerful as they are, have limits. That the universe contains places where our understanding falls away entirely. And it invites us to keep searching, not just to see farther into space, but to see deeper into the nature of existence. A gentle pause before sleep. As you lie back, imagine yourself drifting in that strange, curved space. The stars are gone. The outside universe is no longer visible. There is only the quiet pull toward the heart of the black hole, the place where the river of space-time ends, and where something else, something we cannot yet name, begins. Perhaps it is an ending. Perhaps it is a doorway. Perhaps it is both. And with that thought, we let the question rest, until the next time we dream our way toward the deepest mysteries of the cosmos. Hawking radiation, how black holes slowly fade away. Black holes have a reputation for being eternal. Silent, cold giants that swallow everything and give nothing back. For decades, that was the story. Once something fell inside, it was lost forever. But in the mid-1970s, one man dared to whisper a different ending. His name was Stephen Hawking. And the idea he brought into the world was so strange, so delicate, that at first it seemed like a dream. Black holes could evaporate. A thought born in paradox. The seed of Hawking's idea was planted in a contradiction. Physics has two great storytellers: general relativity, which describes the grand sweep of space and time, and quantum mechanics, which reveals the jittery, unpredictable world of the very small. Each is powerful. Each is beautiful. But they speak different languages, and when they both try to describe a black hole, their voices clash. Hawking wanted to understand what would happen to a black hole when quantum rules were taken seriously near the event horizon, that invisible boundary where nothing can return. The quantum sea in quantum mechanics, empty space is never truly empty. Even in the perfect vacuum between galaxies, tiny flickers of energy bubble in and out of existence. These flickers are called quantum fluctuations. For a brief instant, they can create a pair of particles, one matter, one antimatter. They appear, borrow energy from the vacuum, and almost immediately find each other again, annihilating in a flash that returns the energy. It is like foam on an invisible ocean, always forming, always dissolving. The black hole's interference now, imagine one of these tiny pairs forms right at the edge of a black hole's event horizon. Usually, the two particles would reunite and vanish together. But the black hole's intense gravity can interfere. One particle may fall inward, swallowed forever, while the other escapes into space. From far away, that escaping particle looks like it was emitted by the black hole. And here's the twist: in order for the escaping particle to exist, the one that fell in must have negative energy relative to the outside universe. This negative energy effectively reduces the black hole's mass. Slowly, quietly, it loses weight. A glow from the darkness. This process is what we now call Hawking radiation. It is not a blaze of light, not something you could see with your eyes, but a faint thermal glow, a whisper of warmth seeping from the black hole's edge. For massive black holes, this glow is unimaginably faint. A black hole the mass of the sun would emit less radiation than the tiniest flicker of heat from your skin. The cosmic microwave background, the leftover warmth from the Big Bang, easily drowns it out. But for smaller black holes, the radiation is stronger. And as they lose mass, the process speeds up, until in their final moments, they release a tremendous burst of energy and vanish entirely. Not just theory, Hawking's calculation was meticulous. He combined the curved space-time of general relativity with the jittering, probabilistic dance of quantum fields, a marriage of two theories that rarely meet without argument. What emerged was a consistent, mathematical prediction: black holes are not perfectly black. They radiate. And because they radiate, they can, in principle, disappear. It was a shock to the scientific world. It meant black holes had lifetimes, not infinite reigns. The long goodbye for most black holes, this goodbye is almost unimaginably long. A black hole with the mass of our Sun would take about 10 years to evaporate completely, a number so vast it dwarfs the current age of the universe, which is only about 1/38 times 10 superscript 1 years. Supermassive black holes like the one in the center of our galaxy would take far longer still, 10 superscript 1 years or more. In the deep, deep future, long after stars have burned out and galaxies have drifted apart into darkness, Hawking radiation could be the last light in the universe. The information problem, but Hawking's discovery brought a new mystery, one so puzzling it still stirs debates today. In physics, there is a cherished rule: information cannot be destroyed. The details of how a system began must, in principle, always be recoverable from what it becomes. But if black holes evaporate, what happens to the information about everything that ever fell inside? Does it vanish? If so, the rule is broken and physics as we know it must change. This information paradox has been one of the most enduring puzzles in modern science. Many brilliant minds, including Hawking himself, have wrestled with it. And while there are promising ideas, such as information being preserved in subtle patterns of radiation, a final answer remains elusive. Why it matters: Hawking radiation is more than just a curiosity about black holes. It is one of the few places where gravity, quantum mechanics, and thermodynamics meet in the same equation. It hints that these three great domains of physics are not separate realms, but parts of a deeper, unified reality we do not yet fully understand. And it offers hope that by studying the faint whispers of heat from the darkest objects in the cosmos, we might learn something about the first moments of the universe, and about the nature of reality itself. A universe that lets go. There's something quietly poetic about Hawking's vision. Even the most stubborn, hungry, and secretive things in the universe must one day let go. Black holes, born from the death of stars, will themselves fade into the cool emptiness of space. Their end will not be a violent explosion unless they are very small, but a gradual release of their mass into the surrounding void. It is a slow, patient surrender. The universe, it seems, keeps nothing forever. Drifting into the future as you picture it now, imagine a black hole in the far-off era when the last star has long gone dark. There is no Milky Way anymore, no planets, no warm sunlight. Only scattered remnants of galaxies, and here, a lonely black hole, faintly glowing with Hawking radiation. Its light is not enough to warm a single grain of dust, yet it is the last flicker in a universe grown cold. Over eons beyond counting, it shrinks. Its gravity weakens. And one day, perhaps after 100 trillion years, it releases a final, brief flash, and is gone. The darkness is complete. And the story of that black hole has ended. In the next part of our journey, we will ask, what happens to time inside a black hole? Because time itself plays by different rules there. What happens to time inside a black hole? Time. It is the quiet river in which all our lives flow. We feel its gentle current with every heartbeat, every sunrise, every passing season. But step too close to a black hole, and that river does not flow as it should. It twists. It stretches. It may even break. To ask what happens to time inside a black hole is to step into one of the deepest and most unsettling mysteries in all of physics. It is a question that forces us to let go of the way we usually think about past, present, and future, and to imagine something far stranger. The nature of time. As we know it here, in our familiar world, time feels constant. Your clock ticks the same whether you are standing still or walking slowly through a quiet street. But Einstein taught us that this is only a comforting illusion. In his theory of relativity, time is not a separate thread, it is woven together with space into a single fabric, space-time. And this fabric is not rigid. It bends under the influence of mass and energy. The more massive an object is, the more it warps space-time. And where space-time bends, time itself slows down. This is not just theory, it has been measured. Astronauts aboard the International Space Station age slightly slower than people on Earth's surface. GPS satellites must account for time dilation to stay accurate. But these effects are small. A black hole is another story entirely. Approaching the event horizon, imagine you are falling toward a black hole. From a safe distance, you see it as a dark circle against the stars, a perfect absence of light. Around it may swirl an accretion disk, a storm of gas and dust heated to unimaginable temperatures as it spirals inward. As you fall closer, gravity grows fiercer. Time for you, in your own experience, feels unchanged. Your heart still beats once every second. Your thoughts move at their usual pace. But to a distant observer, someone watching from far away, your time begins to slow. Your movements appear more sluggish, as if you are sinking into syrup. The closer you get to the event horizon, the greater this difference becomes. From their point of view, you will never quite cross that final boundary. You will seem to freeze in place, your image dimming, stretched thin by the black hole's gravity, fading into redder and redder light, until you vanish completely. Inside the event horizon, but your own story does not end there. From your perspective, you cross the event horizon without noticing anything special at that precise moment. No sudden wall, no shimmer. Yet you have passed a point of no return. From here, all possible paths through space-time lead deeper in. No force in the universe, not rockets, not light, not even the strongest magnetic field can carry you back out. And here, time itself changes its role. In a way that is difficult to visualize, the directions of space and time trade places. Outside the black hole, you can choose where to go in space: left, right, forward, back, but you must always move forward in time. Inside, forward in time is now the same as deeper toward the singularity. Falling inward is as inevitable as tomorrow's sunrise once was. The singularity's pull at the very center of the black hole, at least according to classical general relativity, lies the singularity, a point of infinite density, where the known laws of physics break down completely. From the moment you pass the event horizon, your future is the singularity. Not in a few minutes or in a few hours in the way we usually speak of time, but as a certainty built into the structure of space-time itself. For a small black hole, this journey from horizon to singularity might take mere seconds in your own time. For a supermassive black hole, it could take hours. But the ending is the same. Time for the outside universe now. Here is the part that bends the mind. While you are plunging inward and experiencing your own last moments, the rest of the universe is racing ahead. If you could somehow see the outside world, you might witness the far future in fast motion: stars aging, galaxies drifting apart, cosmic events unfolding at breathtaking speed. In theory, you could watch billions of years pass in what feels like minutes. But in reality, the extreme warping of space-time and the blinding radiation near the horizon would likely make such a view impossible for a living observer. Still, the mathematics of relativity leaves open the haunting idea: a black hole is a kind of time machine, but only forward. Is time destroyed inside? The concept of time inside a black hole is slippery. Our usual markers, clocks, planetary orbits, the rising and setting of the sun, no longer work here. Once you pass the event horizon, all future moments lead inward. In this sense, time as we understand it outside the black hole no longer exists. Some physicists suggest that talking about time inside a black hole may be meaningless without a full theory of quantum gravity, the still elusive framework that merges quantum mechanics with general relativity. Others believe that time may continue in some strange, altered form, and that the singularity itself may be replaced by something less final when quantum effects are properly considered. The traveler's experience lets imagine you as that brave or doomed traveler. Crossing the event horizon, you notice no sharp change. But the light from outside grows distorted, warped into a narrow, glowing halo above you. The pull inward is irresistible. It does not feel like falling anymore, it feels like being carried. Time in your mind ticks on. Your thoughts remain your own. But space itself is collapsing toward you. The very meaning of next is becoming strange. And then, ahead, the singularity waits not as a glowing point, but as a region where the concepts of space and time no longer have meaning we can describe. In those final moments, physics is silent. We do not know what happens there. Why time matters in black hole physics. Understanding time inside a black hole is not just an exercise in imagination. It lies at the heart of some of the greatest puzzles in modern science. The information paradox, the question of whether information about fallen matter is lost forever, is tied to how we think about time and causality in such extreme conditions. The quest for a theory of quantum gravity is, in part, a quest to understand what time really is, at its deepest level. And perhaps, hidden inside this mystery, is a clue about the birth of the universe itself, for the Big Bang, in some ways, mirrors a singularity in reverse. A dreamlike ending. So, what happens to time inside a black hole? From outside, it slows, and stops. From inside, it carries you inevitably toward the singularity, as certain as the turning of a page in a book already written. Whether that is truly an end, or a doorway to something else, remains unknown. And perhaps, as you drift toward sleep now, you can picture yourself at the edge of such a place, feeling the strange pull of gravity not just on your body, but on your very moments. The river of time still flows, but here, in the shadow of the black hole, it flows toward the deepest, darkest mystery in the cosmos. In our next chapter, we will explore the idea of the singularity physics point of no understanding, where our equations go silent, and the imagination must take over. The idea of the singularity physics point of no understanding. There are places in the universe where the known laws of nature fail. Not because they are wrong, exactly, but because they cannot speak the language needed there. Their voice fades, and silence takes their place. At the heart of every black hole, according to Einstein's general relativity, there is such a place. We call it the singularity. A word with many shadows. The word singularity sounds almost delicate, like a rare crystal, or the note of a violin. But in physics, it carries a far more unsettling meaning. It is the point, the boundary where space-time curvature becomes infinite. Infinities are warnings. They tell us our equations have gone somewhere they shouldn't. They do not describe a physical thing so much as they describe the breakdown of the map we are using. Imagine you are reading a detailed atlas, but as you approach the edge of the page, the lines twist into nonsense, rivers loop endlessly into themselves, mountains rise to impossible heights. You know this is not the real landscape. It is the map, failing. The singularity is that failure point in our map of space-time. How relativity predicts it. Einstein's general theory of relativity describes gravity not as a force but as the bending of space-time by mass and energy. Under normal conditions, this bending is gentle. A star curves space around it. A planet makes a smaller dent. You and I barely dent it at all. But when enough mass collapses into a small enough space, the curvature steepens without limit. There is no size where the collapse stops, not even the smallest you can imagine. The equations lead to an inescapable conclusion: the mass shrinks to a point of zero volume and infinite density. That point is the singularity. The cosmic irony: the singularity is hidden. Not just by distance, but by the event horizon, the one-way surface around a black hole. Anything crossing that boundary can never return to tell the tale. So the most extreme prediction of relativity is also the one we can never directly see. It is like hearing the final note of a song you can never actually play. Yet, though we cannot see the singularity itself, we can see its effects: the way black holes bend light, the way they pull in matter, the way time slows near their horizons. The singularity may be hidden, but it shapes the world around it. Not just in black holes. Singularities are not confined to black holes. The Big Bang itself is often described as a singularity, the moment when the universe's density was infinite and space was compressed to a single point. In that sense, the singularity is not only an end point, it can also be a beginning. A seed from which an entire cosmos may grow. It is a reminder that our word singularity covers more than one possibility. It could be an ultimate boundary, or a gateway. Inside the horizon, falling toward the point. If you imagine falling into a black hole, you pass the event horizon, and from there, every path through space-time leads to the singularity. The singularity is not something you can avoid once inside. It is not sitting in the center like a planet in space. Instead, it lies ahead in your personal future, as certain as tomorrow, as inevitable as your next heartbeat. For a small black hole, the journey from horizon to singularity may take only milliseconds in your own time. For a supermassive black hole, it could take minutes, even hours. But the end is the same: you meet the place where space and time collapse together. Why physics breaks? There, our current physical theories are built from two great pillars: general relativity, the law of the very large, stars, galaxies, gravity; quantum mechanics, the law of the very small, atoms, particles, probabilities. These two frameworks work beautifully in their own domains. But near a singularity, the scales collide, gravity becomes infinitely strong, and quantum effects become impossible to ignore. The trouble is, the two theories do not fit neatly together. They give contradictory predictions. Trying to apply both at once produces more infinities, more nonsense. That is why many physicists believe the singularity is not a real physical thing, but a sign that our theories are incomplete. Quantum gravity, the missing bridge to truly understand what happens at a singularity. We need a theory of quantum gravity, one that unites the large and the small into a single framework. Several candidates exist: string theory, which imagines particles as tiny vibrating strings, may smooth out the infinite density of singularities. Loop quantum gravity, which treats space itself as made of discrete loops, may prevent space-time from collapsing past a certain point. In these models, the singularity may be replaced by something else, a bounce, leading to another expanding universe. A region of exotic, finite density matter. Or something stranger still, beyond even our current language to describe. The singular beauty of the problem: why do physicists care so deeply about something we can never see? Because singularities are where our understanding fails. They are the here be dragons marks on the map of the cosmos. To solve them is to discover a deeper truth about reality. The singularity at the center of a black hole is not just an astrophysical curiosity, it is a window into the fundamental nature of space, time, matter, and energy. It is, perhaps, the most extreme laboratory the universe offers us. A gentle thought experiment: close your eyes and imagine floating inside a black hole. You are falling, slowly, peacefully, not because you are being torn apart yet, but because time is passing differently for you than for the outside universe. The space around you is curved, bending inward. The light from the outside world is a faint, distorted glow above you. Ahead, there is no visible point, just the knowledge that space and time are collapsing towards something beyond description. You are not falling through space. You are falling into the end of space itself. And in that place, the rules you have always known will no longer apply. The poetry of the unknown. The singularity is a scientific concept, yes, but it is also a poetic one. It represents the ultimate limit of human knowledge. It is the place where our equations, our instruments, our measurements, all fall silent. In its darkness, there may be an answer to how the universe began. Or there may be only more questions. Perhaps one day, we will understand it completely. Perhaps we will discover that what we call a singularity today is just a shadow cast by something far stranger. Until then, the singularity remains, the heart of the black hole. The point of no understanding. In our next chapter, we will step away from the infinite density itself, and look at what happens to matter as it falls, in tracing the journey of particles and light as they cross the event horizon and meet their fate. What happens to matter as it falls in the story of a black hole is not told only in its darkness. It is also written in the long, slow journeys of the things it consumes. Stars, clouds of gas, drifting dust, even the faintest threads of light, all have crossed that invisible border. And though nothing can return, their passage leaves whispers, patterns, a cosmic ballet we can still watch from far away. So, let us drift closer now. Not toward the singularity itself, not yet, but toward the wide, curved mouth of a black hole, and watch what happens to matter as it falls in. The first signs of a hungry giant from a great distance: a black hole is almost invisible. If there is nothing nearby to feed it, it simply waits, hidden in the fabric of space. But when something does come close, a wandering star, a drifting cloud of gas, the quiet ends. Gravity's invisible hand stretches out, catching hold. At first the pull is gentle, like a slow tide. But as the object draws nearer, the force grows, and soon, the infalling matter cannot escape. Yet it does not fall straight in. Rarely does anything meet a black hole head-on. Instead, most matter approaches at an angle, carrying a little sideways motion and orbital drift. That motion changes everything. The birth of the accretion disk. Because of that sideways movement, the falling matter begins to spiral. Faster and faster, it circles the black hole, unable to break free, but not yet plunging in. As more material joins the dance, it flattens into a thin, hot ring, the accretion disk. From a distance, an accretion disk glows like a brilliant halo. It can outshine an entire galaxy, powered purely by gravity. Friction between particles, magnetic turbulence, and shock waves heat the gas until it blazes with X-rays and ultraviolet light. The accretion disk is not the black hole itself. It is the bright, chaotic threshold, the glowing swirl that feeds the darkness. The journey through the disk, if we could shrink ourselves down to the size of an atom of gas and ride along, our journey would be a wild one. At first, far from the black hole, we would orbit in relative calm. The light around us would be bright but steady. Slowly, collisions with other particles would sap our orbital energy, pulling us inward. As we spiral closer, the heat would rise. Temperatures near the inner edge of an accretion disk can reach millions of degrees. Atoms are stripped of their electrons, turning into a plasma, a sea of charged particles whipped into turbulence by magnetic fields. The closer we get, the faster we orbit. Near the inner rim, we would be circling the black hole at nearly the speed of light. Our view would be a dizzying blur of warped space, curved light, and the looming shadow at the center. Crossing the innermost stable orbit in Einstein's curved spacetime, there is a special distance from the black hole, the innermost stable circular orbit, or ISCO. Outside it, matter can circle the black hole for a long time. Inside it, stable orbits are impossible. Once matter crosses that line, the spiral tightens into a plunge. There is no turning back. From the outside, it looks as though the falling material slows, dimming as it approaches the event horizon. Time dilation stretches its motion until it seems to freeze, fading from sight. But in its own frame of reference, the fall continues, quick and unstoppable. Spaghettification, gravity's final embrace inside the event horizon. Gravity's tidal forces can become unimaginably strong, especially for smaller black holes. The difference in gravitational pull between your head and your feet could be so extreme, that it stretches you into a long, thin shape. This process is called spaghettification, a playful name for a merciless effect. For supermassive black holes, this stretching is more gradual. You could cross the horizon without immediately feeling it. But for stellar mass black holes, tidal forces near the horizon are fatal long before you reach the singularity. Matter's fate beyond the horizon. Once inside, matter is cut off from the rest of the universe. It continues to fall toward the singularity, carrying its mass, energy, and information with it. What happens then is a question wrapped in mystery. According to classical relativity, all of it is crushed into the singularity's infinitely small point. According to quantum physics, something more complex and perhaps less final may occur. Some theories suggest that the information carried by falling matter might be preserved in a scrambled form on the event horizon itself, an idea linked to the holographic principle. Others imagine that matter might re-emerge in a different universe entirely, if black holes are gateways. But these remain speculations. From our perspective outside, all we know is that nothing ever returns. The glow before the dark, though the inside is hidden, the process of falling in can be spectacular to watch from afar. As matter in the accretion disk spirals inward, it releases more energy per gram than nuclear fusion in a star's core. That is why black holes can be the brightest objects in the universe, even though the holes themselves are completely black. Jets of high-energy particles can shoot out along the black hole's rotation axis, piercing through galaxies and traveling for thousands of light-years. These relativistic jets are powered not by the hole's interior, but by magnetic fields twisting in the disk's maelstrom. In a way, matter's fall into a black hole is both an ending, and a kind of creation. The light it releases on the way in can shape galaxies, trigger star formation, and heat interstellar gas. A slow cosmic rain, black holes rarely feed in giant gulps. Instead, they sip slowly, drawing in streams of material over millions of years. A single star torn apart by a black hole might feed it for decades. From our viewpoint, the process is like watching a candle burn in deep space. The glow is steady, until the fuel is gone, and darkness returns. The personal view falling together now. Let's imagine, for a moment, what it might feel like to fall in ourselves. We begin far away, drifting slowly toward a dark point in the sky. It is almost invisible, only the faint distortion of background stars hints at its presence. As we get closer, the stars seem to smear and curve. The black circle in the center grows, edged by a glowing ring of swirling light. We feel the tug of gravity deepen, pulling at us with patient strength. Crossing the accretion disk would be like diving into a river of fire. The heat would be unbearable, the glare overwhelming. We would be spun faster and faster, whipped around at nearly light speed. Then a final spiral. A point where the path curves inward and there is no longer any choice. We fall. Outside, the universe watches us fade, until there is nothing left to see. Inside, we still move. Towards something we cannot describe, but must inevitably meet. In our next chapter, we will go deeper still into the final moments before the singularity, tracing the last heartbeat of matter before it reaches the ultimate end. The final moments before the singularity. The journey has been long. We began far away, where a black hole is just a shadow among stars. We have passed through the spiral glow of the accretion disk. We have crossed the event horizon, the point where no light escapes, and we have felt the pull deepen beyond anything the human mind was built to imagine. Now, there is no going back. No sideways escape, no last orbit. Only the final descent toward the most mysterious place in the universe, the singularity. But what, truly, are these last moments like? How does time behave here? What does the world look like when reality itself begins to bend beyond recognition? Let us slow ourselves down, to almost nothing, and follow the fall. A place without outside. Once we are past the event horizon, there is no longer any concept of outside. The universe, for us, has become the interior of the black hole. All light, all space, all directions point toward the same fate, the center. Here, the rules are strange. The coordinates of space-time, as Einstein described them, begin to behave in unfamiliar ways. The direction we used to think of as forward in time now leads us toward the singularity. The direction we once called down is meaningless. The center is future now, not below. This is not a place we can truly picture, but we can feel its pull. Every tick of our clock is also a step closer to the singularity. There is no stopping, no turning around. Time's last stretch from the point of view of a distant observer, our fall inside the black hole is hidden. They see only the moment we cross the horizon, and then nothing. The rest of our journey is cut off, sealed away behind the invisible border. But for us, time continues. We measure it with our own heartbeat, our own thoughts. Yet time here is not the same as before. The closer we get to the singularity, the more the geometry of space-time funnels us inward. Like water rushing down a narrowing funnel, our future is drawn into a single point. If we could watch the clock on our wrist, it would still tick normally, second by second, heartbeat by heartbeat. But we would know that each moment is shorter than the last, because the space in which moments can happen is shrinking. The view around us, there is no way to carry the outside universe with us, but we might still sense the distorted light that fell in before. Strange echoes of radiation, tangled and warped by the black hole's curvature, could flicker in ghostly arcs. In a stellar mass black hole, tidal forces would be extreme here. Every part of us, atoms, molecules, the spaces between them would be stretched and squeezed. In a supermassive black hole, those forces would be gentler at first, so we might travel farther before feeling them. Either way, the view is unlike anything else. We are not surrounded by darkness, but by a shifting haze, the last trapped light swirling inward, the glow of matter falling ahead of us. It is not a horizon we see anymore, it is a narrowing tunnel of existence. Tidal forces, the narrowing funnel. Imagine standing on Earth's surface and feeling gravity pull more strongly on your feet than your head. The difference is tiny here, just enough to keep you grounded. Near a singularity, this difference can grow so enormous that it overcomes the forces that hold your body together. You are stretched not metaphorically, but literally into a thinner and thinner line. This spaghettification is not a violent tearing in the usual sense, but an unavoidable reshaping of matter under gravity's differential pull. In this final region, even atoms themselves could be elongated, electrons stripped away, nuclei crushed together. Approaching infinite density in Einstein's general relativity, the singularity is a place where density becomes infinite. Matter is compressed into a point with zero volume, a concept our minds cannot truly hold. But point here does not mean a speck in space. It is not a location you could point to from outside. It is a boundary in time, the inevitable end of every path forward once you are inside the black hole. Physics, as we know it, breaks down here. Quantum effects, normally too small to matter at large scales, may now dominate. Some scientists believe the singularity may not truly be an infinite point, but something else, a knot of space-time, a loop, a bridge to another region of the cosmos. Yet these are only guesses. No signal can leave this place to confirm them. The last second, if we could somehow mark the moment just before reaching the singularity, what would it be like? For us, the fall might be smooth, no sudden impact, no wall to collide with. Instead, the crushing force would steadily rise until it surpassed the strength of matter itself. There would be no moment to pause and reflect. The singularity is not a place you arrive at, it is the moment your future runs out. Our last second is also the black hole's final act of consumption. Our mass, our energy, and whatever we carried within us become part of its gravitational identity. From the outside, nothing changes. The black hole is just slightly heavier now, its event horizon a little larger. But inside, for us, the journey is over. Beyond the end, speculation and wonder, this is where science meets mystery. Some theories suggest that singularities might be smoothed out by quantum gravity, a yet unknown theory that unites Einstein's relativity with the quantum world. Others imagine that a singularity might connect to a white hole, a hypothetical region where matter is expelled instead of drawn in. In some versions of cosmology, a black hole singularity might even give birth to a new universe, sealed away from ours. We do not know. Perhaps we will never know. The singularity is not only hidden, it may be forever beyond reach. And yet, the mystery itself is part of its beauty. It is the heart of the black hole, the place that reminds us there are limits to our understanding, and that the universe still holds secrets deep enough to swallow light. The final image, so, let us step back in our minds one last time. We began on the quiet edge of space, gazing toward a point of darkness. We followed matter into its spiral, crossed the horizon, and drifted toward the unseen center. We have now reached the last heartbeat of the journey, the place where time itself ends. The singularity does not roar. It does not shine. It waits, silent and absolute, at the end of every path inside the black hole. And in that stillness, we leave our story, for the next dreamer to imagine. The legacy of a black hole. The black hole we have been journeying through has finally claimed us. Our story, as travelers, has ended at the singularity. But the story of the black hole itself continues. Because black holes, despite their silence, leave echoes. Not the kind that bounce through air or stone, but ripples through the very fabric of reality. These echoes, this legacy, shape galaxies, stir stars, bend light, and spark the minds of those who dare to imagine what cannot be seen. Tonight, in the soft darkness of our shared dream, we will drift outward again, not to escape the black hole, but to watch its mark upon the universe it inhabits. A quiet giant at the heart of a galaxy, in the center of most galaxies, including our own Milky Way, lives a supermassive black hole. They are billions of times more massive than our Sunday. And yet, they hide quietly among the stars, their presence known only through the dance of the matter around them. The one in our galaxy, Sagittarius A*, is a patient ruler. It feeds rarely, waiting centuries before swallowing passing clouds of gas or unlucky stars. When it does feed, it flares in radio waves and X-rays, announcing its meal to telescopes across the Earth. Over millions of years, such a black hole shapes the stars around it. It may help keep the galaxy bound together, or even influence how stars are born in its vast neighborhoods. It is strange to think of something so destructive also playing the role of a caretaker, but in the cosmic sense, that is exactly what it does. Galactic sculptors, black holes are not just passive observers of the universe. When they feed hungrily, they can unleash storms of energy powerful enough to shape entire galaxies. Matter spiraling toward the event horizon is superheated to millions of degrees, creating jets of particles that blast outward at near light speed. These jets can stretch for thousands of light years, plowing through interstellar clouds. In doing so, they may trigger the collapse of gas into new stars, or strip away the raw material, halting star birth entirely. Like sculptors with fire instead of hands, black holes carve the shape and destiny of galaxies. The story written in light. Even though black holes themselves emit no light, the story of their lives is written in the light around them. Radio telescopes trace the long tendrils of their jets. X-ray observatories catch the flashes of their feeding. Infrared instruments peer through dust to see stars caught in their gravity. When astronomers first began mapping these signs, they saw patterns. Galaxies with active black holes often glowed fiercely in their centers, while those with quieter ones shone more gently. In this way, the behavior of a single black hole can change the personality of an entire galaxy. The mergers. When giants meet, black holes can grow not only by feeding, but by merging. When galaxies collide, as our Milky Way will one day collide with Andromeda, their central black holes spiral toward each other over millions of years. In the final moments of their dance, they merge in a burst of gravitational waves, ripples in space-time that race outward at the speed of light. These waves, once purely theoretical, have now been detected by observatories like LIGO and Virgo. They are the signature of black holes meeting, joining, and becoming something larger. Each merger leaves behind a heavier, more powerful black hole, and the memory of the waves it sent through the universe. Gravitational waves. The whispers of collisions. Gravitational waves are among the most delicate things ever measured. They stretch and squeeze space itself, but by amounts smaller than the width of a proton. And yet, they tell us stories that no other messenger can. In 2015, the first detection of such a wave confirmed Einstein's century-old prediction. Since then, astronomers have recorded dozens more, each one revealing a hidden event billions of light-years away. Black holes, in their final violent moments, have become poets, sending ripples instead of words, letting the universe carry their story forward. Hawking skipped black hole evaporation for much of the 20th century. Black holes were thought to be eternal. Nothing, it was believed, could escape them, not even time itself. Then, in 1974, Stephen Hawking revealed something astonishing. Through the strange dance of quantum particles at the event horizon, black holes should slowly lose mass, radiating away their energy. This Hawking radiation means that black holes are not forever. Given enough time, far longer than the current age of the universe, they will fade away into nothing. Even the mightiest supermassive black holes will one day vanish, leaving only the faintest whisper of heat in the cold, dark future of the cosmos. The long goodbye. Imagine the last days of a black hole. For billions of years, it has been a giant, shaping galaxies, swallowing stars, merging with others. Now, in the far future, the universe is nearly empty. The last stars have cooled, the last galaxies have drifted apart. The black hole radiates away its mass, at first slowly, then more quickly as it shrinks. In its final instant, it releases a burst of energy, the last light in a universe grown dark. And then, it is gone. The legacy it leaves is not only in the stars it shaped or the galaxies it influenced, but in the proof that even the most powerful things in the universe are temporary. The human legacy, our connection to the dark black holes, also leave a legacy in us. We, the observers, the dreamers, the scientists, have built our understanding of them piece by piece. They have challenged our imagination, forcing us to expand our concepts of space, time, and reality itself. They have taught us humility, that the universe contains mysteries beyond our reach. They have also taught us persistence, that even when we cannot touch a thing, we can still learn from the light it bends, the waves it sends, and the shadows it casts. The endless inspiration from science fiction to poetry, from equations on a chalkboard to the quiet moments under a starry sky, black holes inspire us to think beyond the horizon of the known. Every question they raise: what lies beyond the singularity? Could they connect to other universes? Do they store the history of what they consume? Becomes fuel for the next generation of explorers. And so, their legacy is not only carved in galaxies, but also in the minds of those who will never stop wondering. The final word: a black hole begins as a dying star. It grows by feeding, by merging, by shaping its galaxy. It influences the dance of matter and the birth of light. It may last for trillions upon trillions of years, but even it will one day fade. Its legacy is written in the stars, the ripples of space-time, the slow breath of Hawking radiation, and in our endless desire to understand what lies inside the darkness. As we close this chapter, remember, the black hole we imagine tonight is still out there, silent, patient, leaving its mark on the universe and on us. The stars have dimmed in our story tonight. The last echoes of light from our imagined journey drift quietly into the distance. We have wandered from the birth of a black hole, to the swirling storms at its edge, and finally, into the deepest, most silent center. We have felt the pull of gravity so strong it bends time itself. We have watched matter vanish beyond the event horizon, knowing we could never follow it back. And yet, in telling this story, we did follow it. Not with ships or instruments, but with thought, and with the quiet courage of curiosity. The black hole was our destination. But along the way, we found something else: the beauty of not knowing everything. It is a strange comfort, to realize that the universe holds places that will forever be beyond our reach. That there will always be mysteries, and that we are allowed to dream about them. Tonight, you and I have drifted together through those dreams. Through ancient starlight, cosmic winds, and the dark heart of the unknown. And now, the story closes. But the black hole remains far away, silent, turning slowly in the night, pulling in matter, bending light, leaving ripples in a universe that keeps unfolding. One day, perhaps far in the future, another dreamer will listen to this story. And in their mind's eye, they too will drift toward the edge where time slows, where light fades, where the greatest secrets are kept. Until then, rest. Let the pull of sleep take you the way gravity takes starlight, softly, inevitably, into the quiet. Good night, from the dreamy scientist. And thank you, for traveling so far with me.